Hello there, and welcome to Science for Sleep, where curiosity gets cozy, and even the vastest mysteries of the universe are allowed to unfold at an unhurried, gentle pace. Tonight's journey drifts far beyond our planet, past the quiet glow of familiar stars, and into a region of space where something extraordinary once happened. Not a violent explosion, not a sudden flash, but a slow, immense interaction between structures so large that even light itself needed millions of years just to cross them. The subject waiting for us is something called the bullet cluster, a name that sounds sharp and fast, but hides a story that is anything but hurried. It is a place where entire galaxies pass through each other, where matter separated in ways that seemed impossible, and where scientists watching from millions of light years away realize they might be seeing something invisible for the very first time. Before we ease into that moment, let me ask you something simple. Where are you listening from tonight, and what time is it in your little corner of the world? Perhaps it's late, and the day has already folded itself into quiet. Or maybe it's earlier, and this is just a pause between one moment and the next. Either way, it's a small reminder that while we sit here, grounded in our own routines, the universe is carrying on with events so vast and slow that they almost feel timeless. If you find this journey calming or interesting, or simply a gentle way to wind down, you might consider liking the video or subscribing. It helps this quiet space reach others who might need a moment like this too, and if not, that's perfectly fine as well. Just settle in, get comfortable, and let your thoughts slow down a little. Now, imagine for a moment something that seems almost impossible. Two enormous cities drifting toward each other, not on Earth, but in space. Not made of buildings and streets, but of galaxies. Each city contains hundreds of billions of stars, each star possibly surrounded by planets, each planet carrying its own quiet story. And these two vast collections are not rushing, not colliding in a dramatic crash, but simply passing through one another, like two clouds drifting in opposite directions. At first, that idea might sound strange. When we think of collisions, we imagine impact, destruction, things breaking apart. But on the scale of galaxy clusters, space is so empty that even when two entire clusters meet, the stars within them almost never touch. The distances between stars are so immense that the galaxies slip past each other like ghosts. This is the first thing that makes the bullet cluster so unusual, not because it collided, but because of what didn't collide. The galaxies themselves, those bright islands of stars, passed through with very little disturbance. If you were somehow able to stand on a planet within one of those galaxies, you might not even notice anything dramatic happening at all. The night sky would shift slowly, unfamiliar constellations drifting into view, but there would be no sudden crashes, no fiery impacts. Yet something else was there, something that didn't behave the same way. Between the galaxies, filling the space within each cluster, there is a thin, extremely hot gas. This gas doesn't glow in visible light, so we can't see it with our eyes, but it shines brightly in X-rays. It is made of ordinary matter, the same kind of atoms that make up stars, planets, and even you. And unlike the galaxies, this gas does not pass through quietly. When the two clusters met, their gas clouds slammed into each other. Not instantly, not explosively, but with enough resistance to slow them down. Imagine two large clouds of smoke drifting together and then pushing against each other, compressing, heating, glowing more intensely as they interact. That is closer to what happened here. So now we have two different behaviours happening at once. The galaxies move forward, largely unaffected, continuing on their paths. The gas, on the other hand, lags behind, slowed by the interaction. Already this creates a strange separation. The visible galaxies are no longer aligned with the majority of the ordinary matter, which is trapped in that glowing heated gas between them. But the story doesn't stop there. In fact, this is only the beginning of what made the bullet cluster so important. Because when scientists looked closer, they noticed something that didn't fit any simple explanation. To understand why, it helps to take a step back and think about how we usually understand mass in the universe. When we look at something, whether it's a star or a galaxy, we assume that most of its mass is tied to what we can see. Light becomes a kind of guide, a way of telling us where matter is. If you see a bright cluster of galaxies, you expect that's where the mass is concentrated. If you see a glowing cloud of gas, you assume that's where the bulk of the matter lies. But what if that assumption isn't always true? This question had been quietly growing in astronomy for decades before the bullet cluster was ever observed. When scientists studied the motion of galaxies, they noticed something odd. Galaxies were rotating faster than they should, based on the visible matter alone. Clusters of galaxies were holding together more tightly than expected. It was as if there was extra mass, something invisible, contributing to the gravitational pull. This unseen component was given a simple name: dark matter. Not because it is dark in the sense of being shadowy or black, but because it does not interact with light. It doesn't emit it, reflect it, or absorb it. It is, in a very real sense, invisible. For a long time, dark matter remained an idea supported by indirect evidence. It explained observations, but it had not been directly separated from normal matter in a way that could be clearly seen. And that is where the bullet cluster changes everything. As the two clusters passed through each other, something remarkable happened. The galaxies moved ahead. The gas slowed down and stayed behind. But the gravitational pull, the mass itself, did not stay with the gas. Instead, it followed the galaxies. This is the moment where things become truly interesting, because gravity gives us a way to detect mass even when we cannot see it. Through a phenomenon called gravitational lensing, massive objects bend the path of light passing near them. If you observe distant galaxies behind a massive cluster, their light will appear slightly distorted, stretched, or shifted due to the gravitational influence of whatever lies in between. By carefully measuring these distortions, scientists can map where the mass is, even if that mass is invisible. When they did this for the bullet cluster, they expected to find the mass aligned with the gas, since the gas contains most of the visible ordinary matter. But that's not what they found. The mass was concentrated around the galaxies, not the gas. This meant that something unseen had passed straight through the collision, unaffected just like the galaxies themselves, and that something carried most of the mass. It's worth pausing here for a moment, because this is one of those quiet turning points in science, where a long-standing question suddenly gains a much clearer answer. If all the mass in the cluster were made of normal matter, it would have behaved like the gas. It would have slowed down, interacted, stayed behind. But instead, most of the mass behaved as if it didn't interact at all, except through gravity, which is exactly how dark matter is expected to behave. So rather than being just a theoretical idea used to explain odd observations, dark matter was now being revealed in a more direct way, not seen in the traditional sense, but mapped, separated, and identified through its gravitational effects. It's almost like watching footprints appear in the snow, even though you can't see the person making them. The bullet cluster became one of the clearest pieces of evidence that dark matter is not just a mathematical convenience, but something physically real, something that exists independently of the ordinary matter we're familiar with. And yet, even with this clarity, there is something quietly strange about the whole situation. Because what we're really seeing here is a universe where most of the matter doesn't interact the way we expect. It doesn't collide, it doesn't glow, it doesn't slow down when things crash into it. It simply moves, guided by gravity, passing through everything else as if it barely notices. If you imagine the universe as a kind of layered structure, the visible part, the stars, the gas, the galaxies, might be only a small fraction of what is actually there. Beneath it, or perhaps alongside it, is something far more substantial, shaping everything, but remaining hidden. And the bullet cluster gave us a rare glimpse of that hidden structure, not by revealing it directly, but by showing us how it behaves when everything else is forced out of alignment. From here, the story begins to open outward. Once you accept that most of the mass in these clusters is invisible, new questions start to form. What exactly is dark matter made of? Why doesn't it interact with normal matter? How does it shape the formation of galaxies and the structure of the universe itself? Something rather unexpected begins to happen when you look closely at how galaxies move through the universe. It doesn't match the kind of collisions we're used to imagining. There's no crashing sound, no sudden impact, no dramatic explosion lighting up the darkness. Instead, what unfolds is quiet, slow, and almost strangely polite, as if two enormous structures simply acknowledge each other and continue on their way. If you picture two galaxies heading toward one another, your first instinct might be to imagine chaos. After all, each galaxy contains hundreds of billions of stars. It feels like something that large should collide in a spectacular way, like two storms meeting in the sky. But the truth is much calmer than that, and in some ways, much more surprising. The key to understanding this lies in just how much empty space exists inside a galaxy. Even though galaxies look dense and bright when we see them from afar, the stars within them are separated by distances that are difficult to fully grasp. If our sun were the size of a small coin placed on a table, the nearest star would be another coin sitting several kilometers away. That's not just a little bit of space. That's vast open distance. So when two galaxies drift into one another, the stars don't behave like particles in a crowded room. They behave more like distant travelers crossing paths in an enormous, mostly empty landscape. As a result, the chance of two stars directly colliding is incredibly small. Not just unlikely, but so rare that it might not happen at all, even during an event involving billions upon billions of stars. Instead, the galaxies pass through each other. That's why people sometimes describe them as moving like ghosts. Not because they are insubstantial, but because they don't interact in the way we expect. They overlap, they interweave, and then they continue on, each star following its own path, guided by gravity but rarely interrupted by direct contact. If you were somehow standing on a planet in one of those galaxies, you might not even realize a collision was happening. The night sky would slowly change. New stars would appear, unfamiliar patterns would drift across the darkness, but there would be no sudden catastrophe, no shock wave, no visible crash. It would feel more like a slow transformation than an event. And yet, something is still happening beneath that calm surface. Because while the stars pass by one another without much interference, gravity is still at work. Every star, every cloud of gas, every bit of matter is pulling on everything else. Over time, these gravitational interactions can stretch galaxies, distort their shapes, and create long, elegant streams of stars that trail out into space. These are sometimes called tidal tails, though they have nothing to do with oceans. They form because gravity doesn't act evenly across a galaxy. The side closest to another galaxy feels a slightly stronger pull than the side farther away, and that difference begins to tug the structure apart slowly and gently. So while the stars themselves don't collide, the galaxies as a whole begin to change. Spiral arms can become elongated, central regions can shift, entire galaxies can merge over time, not through impact, but through a gradual process of gravitational interaction that takes millions or even billions of years. It's a kind of collision that unfolds so slowly that it almost escapes the meaning of the word. And this is where the bullet cluster becomes especially interesting, because it involves not just galaxies, but entire clusters of galaxies, each one containing hundreds or even thousands of individual galaxies, along with something else that plays a crucial role. To understand that, it helps to think about what else exists inside a galaxy cluster besides stars. Between the galaxies, there is a thin, diffuse gas. It doesn't look like much in visible light, but it carries a significant amount of ordinary matter. In fact, in many clusters, this gas accounts for more mass than all the stars combined. It is incredibly hot, heated to millions of degrees, and it emits X-rays rather than visible light. So while it remains invisible to our eyes, it becomes very bright when observed with X-ray telescopes. This gas behaves very differently from stars. Unlike stars, which are compact and widely separated, the gas is spread out and continuous. When two clusters meet, their gas clouds don't pass through each other easily. Instead, they interact. They slow down, they compress, and they heat up even further. So now you have two very different components moving through the same event. The galaxies glide past one another, barely noticing the encounter. The gas clouds, on the other hand, collide, resist, and lag behind. Already, this creates a kind of separation within the cluster. But before we go further into that, it's worth lingering for just a moment on the idea of galaxies passing like ghosts, because it challenges something very basic about how we think of matter. We tend to associate matter with solidity, with resistance, with the idea that objects cannot pass through one another. That intuition works well in our everyday lives, where objects are dense and interactions are immediate. But on cosmic scales, that intuition begins to fade. The universe is not a crowded place. It is mostly empty, with matter spread out across enormous distances. And because of that, interactions that seem inevitable on small scales become rare on large ones. Even entire galaxies, structures so vast that they take light tens of thousands of years to cross, can move through one another without direct collision. It's a reminder that scale changes everything. The same laws of physics apply, but their effects look very different depending on the distances and densities involved. What feels solid and unavoidable in one context becomes sparse and unlikely in another. And this quiet, ghost-like passage of galaxies is not just a curiosity. It is the foundation for understanding what happened in the bullet cluster. Because if the galaxies had collided directly, if everything had behaved like solid objects, the separation observed later would not make sense. The fact that galaxies pass through each other so easily is what allows us to see the differences between the various components of the cluster. It creates a kind of natural experiment, one that separates stars, gas, and something else that we cannot see. You can think of it like pouring two different liquids into each other, except instead of mixing, they separate based on how they interact. One flows freely, the other slows down, and over time patterns emerge that reveal their hidden properties. Except here, the liquids are galaxies, gas, and dark matter, and the scale is measured not in meters, but in millions of light years. It's also worth noting that galaxy collisions are not rare in the universe. They happen all the time, though on timescales far longer than a human lifetime. Our own galaxy, the Milky Way, is on a slow path toward a future interaction with the Andromeda Galaxy. That event will take billions of years to fully unfold, but when it does, the same principles will apply. The stars will pass through each other, the shapes of the galaxies will change. Over time, they may merge into a single, larger galaxy. And if there are observers somewhere within that future galaxy, they might watch the sky shift and change, unaware that they are part of a cosmic interaction already in progress. So in a sense, the bullet cluster is not entirely unique. It is one example of a process that happens throughout the universe. What makes it special is not the collision itself, but what it revealed. Because in this particular case, the conditions were just right. The clusters moved at high speed. The gas was clearly visible in X-rays, and the separation between different components became large enough to measure. It's as if the universe set up a demonstration, not intentionally of course, but in a way that allowed us to see something that had been hidden, and that something begins to emerge more clearly when we look beyond the stars themselves. Because while galaxies pass like ghosts, there is still a question left hanging quietly in the background. If most of the visible matter is either in stars or in gas, and if those two behave differently during a collision, then where does the majority of the mass actually go? Does it follow the gas, slowed down by interaction? Or does it move with the galaxies, unaffected by the collision? That question might not seem urgent at first. It sits there quietly, almost unnoticed, like a detail waiting to be explored. But as we move forward, it becomes the central mystery, because the answer is not what anyone expected. and understanding that answer requires us to take a closer look at something that cannot be seen at all, something that does not glow, does not collide, and does not behave like the matter we're familiar with. It simply exists, shaping everything around it, quietly guiding the motion of galaxies, and leaving behind traces that can only be detected if you know where to look. There is a quiet assumption most of us carry without really noticing it. When we look at something, we expect that what we see is what is there. A bright object must be heavy, a faint one must be light, and if something is completely invisible, then surely it must not matter very much at all. That idea works perfectly well in everyday life. A table feels solid because it is. A stone has weight because we can feel it in our hands. Even something like air, which we can't see, still makes itself known when the wind picks up or when we take a breath. But when we begin to look outward, beyond Earth, beyond even our own galaxy, that simple relationship between appearance and mass starts to loosen. Astronomers, for a long time, believed that the universe was made mostly of the same kinds of matter we are familiar with. Stars, planets, gas, dust, all of it glowing or at least detectable in some way. If you could measure the light, you could estimate how much matter was there. It felt reasonable, almost obvious. And for a while, that assumption seemed to work. When scientists observed stars within galaxies, they could measure how fast those stars were moving. Using the laws of gravity, they could then estimate how much mass was needed to keep those stars in orbit. The idea is simple. The faster something moves in a gravitational system, the more mass must be present to hold it in place. It's a bit like watching a stone tied to a string and spun in a circle. The faster it spins, the tighter the pull you feel in your hand. That pull tells you something about how strong the forces are, even if you can't see them directly. So astronomers began applying this idea to galaxies. They measured how stars moved, especially those far from the centre of a galaxy, where the gravitational pull should be weaker. Based on the visible matter alone, those outer stars should move more slowly. There simply shouldn't be enough mass out there to keep them moving quickly. But that's not what they found. Instead, stars at the edges of galaxies were moving much faster than expected. Not just a little faster, but significantly so. It was as if there was extra gravity present, something unseen, holding everything together more tightly than it should. At first, this was puzzling, but not immediately alarming. Maybe there was more ordinary matter than we could see. Perhaps faint stars, cold gas, or dust that didn't emit much light. It seemed reasonable to assume that the missing mass was simply hiding. But as observations improved, that explanation became harder to maintain. The amount of unseen ordinary matter required to explain these motions was enormous. Far more than could be accounted for by faint stars or gas. And even when astronomers looked carefully in other wavelengths, trying to detect this hidden matter, it still didn't show up in sufficient quantities. The universe, it seemed, was heavier than it looked, and not by a small margin. In fact, the visible matter, everything we can see, stars, galaxies, glowing gas, makes up only a small fraction of the total mass needed to explain the motions we observe. That realization didn't arrive all at once. It built gradually across different observations, different galaxies, different clusters. Each time the same pattern appeared. There was more gravity than visible matter could account for. This unseen component was given a name, not because it was fully understood, but because it needed to be described. Dark matter. The name is simple, almost understated. It doesn't tell us what it is, only what it isn't. It isn't luminous. It doesn't interact with light. It doesn't glow, reflect, or absorb in ways we can easily detect. But it does have mass. And because it has mass, it exerts gravity. That gravity is what holds galaxies together, what influences the motion of stars, what shapes the structure of clusters, and what subtly bends the path of light travelling across the universe. At this point, you might wonder how something invisible can be studied at all. The answer lies in the way gravity leaves traces. Even if you cannot see an object, You can still observe its effects. If something pulls on nearby matter, if it changes the motion of stars, if it bends light from distant galaxies, then it reveals itself indirectly. It's a bit like noticing footprints in fresh snow. You don't see the person who made them, but you know they were there. You can follow their path, estimate their weight, even guess their direction. Dark matter leaves similar footprints, not in snow, but in the structure of the universe itself. One of the clearest places to see these effects is in galaxy clusters. These clusters are the largest gravitationally bound structures in the universe. They contain hundreds or even thousands of galaxies, along with vast amounts of hot gas and, as it turns out, even larger amounts of dark matter. When astronomers measure the motion of galaxies within a cluster, they find that the visible matter alone is not enough to keep the cluster together. Without additional mass, the galaxies would simply drift apart, but they don't. The cluster remains bound, held together by gravity that cannot be fully explained by what we can see. This is where the idea of hidden weight becomes more than just a metaphor. It becomes a measurable reality. If you are somehow able to weigh a galaxy cluster using its gravitational effects, you would find that most of its mass is not in stars or gas. It is in something else, something invisible, something that does not interact in familiar ways. And this hidden weight is not evenly distributed. It forms large halos around galaxies and clusters, extending far beyond the visible edges. These halos act like scaffolding, providing the gravitational framework within which galaxies form and evolve. Without dark matter, galaxies as we know them might not even exist. The stars would not have clumped together in the same way. The structures we see, spiral arms, clusters, vast filaments stretching across the cosmos, might never have formed. So in a sense, dark matter is not just an addition to the universe. It is a foundational component. And yet, despite its importance, it remains elusive. We cannot see it directly. We cannot capture it in a detector with certainty. We can only infer its presence through the way it shapes everything else. This creates a strange situation. We live in a universe where most of the matter is invisible, where the majority of mass does not interact with light, where the structures we see are guided by something we cannot directly observe. It's a bit like living in a house where most of the walls are invisible, but still determine the shape of every room. You move through it, you interact with it, but you never quite see the full structure. And this is where the bullet cluster becomes so important, because it offers a rare opportunity to separate these components, to see what happens when visible matter and dark matter are pulled apart by a cosmic event. Up until this point, the evidence for dark matter had been indirect but consistent. It explained galaxy rotation, cluster dynamics, and large-scale structure. But there was always a lingering question. Could there be another explanation? Some scientists wondered if perhaps our understanding of gravity itself was incomplete. Maybe the laws of gravity behave differently on large scales. Maybe the extra motion we observe doesn't require unseen matter, but rather a modification of the rules we use to describe motion. This idea led to alternative theories, attempts to explain the observations without invoking dark matter, and for a time these ideas remained viable because the evidence, while strong, was not yet decisive. But the bullet cluster changes that, because in this particular case, the hidden weight does something very specific. It moves in a way that can be mapped, separated, and compared to the visible matter. It doesn't stay with the gas. It doesn't behave like ordinary matter. It follows its own path, guided only by gravity, passing through the collision without slowing down. This creates a situation where the invisible mass becomes distinguishable from the visible mass, not directly visible, but spatially separated. And once that separation is observed, it becomes much harder to explain the phenomenon without invoking something like dark matter. It's as if the footprints in the snow suddenly diverge from the visible path, revealing that the traveller was not where you thought they were. That moment when the hidden weight reveals itself through its behaviour is what makes the bullet cluster such a powerful piece of evidence. But before we get there, it helps to fully appreciate just how much of the universe this hidden component represents. When scientists estimate the total composition of the universe, they find that ordinary matter, everything we are familiar with, makes up only about 5%. The rest is dominated by dark matter and something even more mysterious called dark energy. So the vast majority of the universe is not only invisible, but also fundamentally different from the matter that makes up stars, planets, and people. This shifts our perspective in a subtle but profound way. What we see, the bright stars, the glowing galaxies, the luminous gas, is only a small part of the whole. The universe, in its full complexity, is largely hidden. And yet, through careful observation, through the study of motion, gravity, and light, we can begin to uncover its structure. We can trace the outlines of something we cannot see, like mapping the shape of a room in complete darkness by feeling the walls. When two massive clusters pass through each other, when galaxies drift like ghosts and gas slows and lingers, the hidden weight has nowhere to hide. It reveals itself not through light, but through motion, through gravity, through the quiet, persistent pull that shapes everything around it. There's a certain way we tend to think about motion, especially when large things are involved. We imagine speed, impact, suddenness. Cars collide, objects crash, events unfold in sharp, decisive moments. Even the phrase traffic accident brings to mind something abrupt, something loud, something over in an instant. But in the universe, motion follows a very different rhythm. When enormous structures move, they do so slowly, almost imperceptibly, guided by gravity over immense stretches of time. And when those structures meet, what we might call an accident does not happen in seconds or minutes, but over millions of years. So when we talk about the bullet cluster as a kind of cosmic traffic accident, it's worth holding that contrast gently in mind. Nothing here is rushed. Nothing is sudden in the way we usually understand it. And yet, what unfolded was still an encounter between two massive systems, each carrying enormous amounts of matter, each moving with significant velocity relative to the other. To begin picturing it, imagine two galaxy clusters approaching one another across space. Each cluster is not a single object, but a vast collection. Hundreds of galaxies, each containing billions of stars, all bound together by gravity. Surrounding and filling the space between those galaxies is a thin, extremely hot gas, and beyond that, extending invisibly, is the halo of dark matter that gives the cluster most of its mass. Now imagine these two clusters drifting toward each other, not in a straight line with perfect symmetry, but along a slightly offset path, like two slow-moving currents in a very large ocean. They have been moving this way for a long time, drawn together by gravity. There is no sudden decision point, no clear moment where the collision begins. It is more like a gradual approach, a closing of distance that takes place over tens or hundreds of millions of years. If you could observe this from a distance, watching in real time, it would feel almost static. The clusters would inch closer, their galaxies shifting positions so slowly that you might wonder if anything was happening at all. But over long enough periods, the movement becomes undeniable. Eventually, the outer regions of the clusters begin to overlap. The gravitational fields start to interact more strongly. Galaxies from one cluster begin to enter the space of the other, passing through without direct collision, as we've already seen. And then, at the core of the encounter, something more noticeable begins to happen. The gas clouds within each cluster, those vast reservoirs of hot diffuse matter, do not pass through each other easily. Unlike stars, which are separated by immense distances, the gas is continuous. When the two clusters meet, their gas components interact directly. They push against each other, they compress, they heat up. This is where the traffic accident analogy becomes useful, not because there is a sudden crash, but because there is resistance. Something slows down, something piles up, something lingers where it might otherwise have continued. The gas from each cluster acts a bit like two slow-moving fog banks, drifting into each other and then compressing into a denser, brighter region where they meet. As this happens, shock waves form within the gas. Not shock waves in the explosive sense we might imagine on Earth, but gradual changes in pressure and temperature that propagate through the medium. In the case of the bullet cluster, this effect is especially pronounced. One of the clusters appears to have moved through the other at a relatively high speed, creating a distinct feature in the gas, a kind of bow-shaped shock front, similar in principle to the wave that forms at the front of a boat moving through water. This is part of why it was given the name bullet. Not because anything was fired, but because one cluster seemed to have passed through the other in a way that created a leading edge, a visible front in the gas that resembles the shape of something moving swiftly through a medium. And yet, even here, the speed is relative. On cosmic scales, what we call fast might still take millions of years to fully unfold. The motion is continuous, steady, and governed entirely by gravity. While the gas slows and compresses, something else continues forward. The galaxies themselves, those collections of stars we might expect to be most affected, move on with relatively little resistance. They pass through the interaction region, emerging on the other side, their paths only slightly altered by gravitational effects. So now, after the main phase of the encounter, we begin to see a separation. The gas, slowed by interaction, remains closer to the centre of the collision. It glows brightly in X-rays, marking the region where the two clusters' ordinary matter has interacted most strongly. The galaxies, meanwhile, have moved ahead, continuing their journey, carrying with them only a small fraction of the total mass. This alone would be an interesting observation, but it is not yet the full story. Because the most important part of the cluster, the part that carries the majority of the mass, does not behave like the gas. And it does not behave exactly like the galaxies either, at least not in a way that is immediately visible. To understand what happened, we need to consider how scientists observed these clusters in the first place. When astronomers look at something like the bullet cluster, they are not relying on a single type of observation. They combine data from different instruments, each sensitive to different aspects of the cluster. Optical telescopes show the galaxies, the stars that emit visible light. These appear as distinct points or smudges, clustered together in certain regions. X-ray observatories reveal the hot gas, which emits strongly at high energies. This gas forms a kind of glowing cloud, often centered between the galaxies. And then there is gravitational lensing, which does not depend on light emitted by the cluster itself, but on how the cluster bends the light from objects behind it. By measuring these distortions, scientists can map the distribution of mass, regardless of whether that mass is visible. So when the bullet cluster was observed using all three of these methods, something striking appeared. The galaxies were in one place, the gas was in another, and the mass, as revealed by gravitational lensing, was aligned with the galaxies, not the gas. This is where the traffic accident reveals something deeper. If all the mass in the cluster were tied to ordinary matter, it should have followed the gas. After all, the gas contains most of the visible matter, and it is the component that interacted most strongly during the collision. But instead, the majority of the mass continued forward, passing through the collision region along with the galaxies. It did not slow down, it did not pile up, it behaved as if it were almost completely unaffected by the interaction. This is not what you would expect from normal matter. It is, however, exactly what you would expect from dark matter. Because dark matter, as far as we understand, does not interact through electromagnetic forces. It does not collide in the same way gas does. It does not experience pressure or friction in the way ordinary matter does. It interacts primarily through gravity. So when two clusters pass through each other, the dark matter halos associated with each cluster would move forward, largely unaffected, just like the galaxies. The gas, on the other hand, would collide and slow down. And that is precisely what we observe. This separation between the visible gas and the inferred mass is the key feature of the bullet cluster. It is what turns a slow, quiet, cosmic encounter into something much more significant. Because it provides a clear visual distinction between ordinary matter and something else. Something invisible. Something that carries most of the mass. Something that passes through collisions without slowing down. If you step back and think about it, it's a remarkable situation. The universe has set up a kind of natural experiment, one that we could never recreate ourselves. Two massive systems collide, their components respond differently, and the result is a separation that reveals the hidden structure of the clusters. It's as if the ingredients of the universe have briefly sorted themselves, allowing us to see which parts belong to which category. And once you see that separation, it becomes very difficult to ignore, because it suggests that the majority of matter in the universe is not like the matter we are made of. It does not glow. It does not collide in the same way. It does not behave like anything we encounter in everyday life. It simply moves, guided by gravity, shaping the structure of the cosmos from behind the scenes. The bullet cluster, then, is not just an interesting collision. It is a moment where the hidden weight of the universe becomes visible through its effects. Up to this point, everything we've talked about might still feel a little abstract. Galaxies passing through one another, gas slowing down, invisible mass continuing forward. These are ideas built from physics, from reasoning, from patterns in data. But at some point, someone had to actually look. Someone had to point telescopes toward this distant region of space and ask a simple question: what is really there? And the answer did not come from just one view, or one image, or one kind of light. It came slowly, carefully, by layering different ways of seeing the universe on top of each other, until a clearer picture began to form. Let's begin with what we would notice first if we were looking through a traditional optical telescope. In visible light, the bullet cluster appears as a collection of galaxies. Small, scattered points of brightness, some faint, some slightly more defined, each one containing billions of stars. There is no obvious drama in this view, no clear sign of a collision, no explosion or disruption that immediately stands out, just galaxies. They sit in two loose groupings, slightly offset from one another, as if they had drifted past and continued on their way. If you didn't know what you were looking at, you might not suspect anything unusual at all. And that's important, because it reminds us that the most visible part of the universe is not always the most informative. Now, if we shift our gaze to something more specialized, the picture begins to change. Astronomers use instruments that can detect X-rays, a form of light that our eyes cannot see. One of the most important tools for this is the Chandra X-ray Observatory, which orbits above Earth's atmosphere, free from the interference that would block these high-energy signals. When the bullet cluster is observed in X-rays, it looks completely different. Instead of scattered points of light, we see a broad glowing cloud. This is the hot gas we mentioned earlier, heated to millions of degrees, shining brightly in X-ray wavelengths. And here, something immediately stands out. The gas is not centered on the galaxies. Instead, it is concentrated in a region between them, forming a kind of luminous bridge or central mass that appears to lag behind the visible galaxies. This alone is already a clue that something unusual has happened. The gas has clearly interacted, slowed down, and settled in a different location than the galaxies themselves. But even this is not the full story. Because while optical images show us the galaxies, and X-ray images show us the gas, neither of these tells us directly where the mass is. For that, astronomers turn to a different method entirely, one that doesn't rely on the cluster emitting light at all. This is where gravitational lensing comes into play. It's a subtle effect, one that requires careful measurement, but it provides something incredibly valuable. A way to map mass, even if that mass is completely invisible. Here's how it works in a simple sense. Light from distant galaxies travels toward us across vast distances, If that light passes near a massive object like a galaxy cluster, its path is bent slightly by gravity. The cluster acts like a lens, distorting the images of the background galaxies. These distortions are not random. They follow patterns that depend on how mass is distributed within the cluster. By analysing many background galaxies and measuring how their shapes are stretched or shifted, astronomers can reconstruct a kind of mass map of the cluster, not based on what is seen directly, but based on how it affects light passing through it. When this technique was applied to the bullet cluster, the results were striking. The mass was not located where the gas was. Instead, the strongest gravitational lensing signals were found in regions aligned with the galaxies. So now we have three different views of the same system. The optical view shows galaxies in two main groupings. The X-ray view shows hot gas concentrated between them. And the lensing map shows that most of the mass is located with the galaxies, not the gas. This is where the observations begin to form a coherent picture. If everything in the cluster were made of ordinary matter, the mass should align with the gas. After all, the gas contains the majority of the visible baryonic matter. It is the component that collided, slowed down, and remained in the centre. But the mass does not follow the gas. It follows the galaxies. And the galaxies, as we've seen, pass through the collision with relatively little interaction. So whatever is carrying most of the mass must also have passed through in the same way. It must not interact strongly with itself or with ordinary matter, at least not in the way the gas does. This is where the observations become more than just images. They become evidence. Because what we are seeing is not just a cluster of galaxies. We are seeing different components of the universe behaving in different ways and separating as a result. The galaxies mark one component, the gas marks another, and the mass map reveals a third, one that cannot be directly seen. It's almost like watching a scene where different materials respond differently to the same event. Some slow down, some pass through, some linger, and by observing those differences you begin to understand what each material is like. In this case, the materials are forms of matter, and the event is a collision between clusters. Another detail worth noticing is the shape of the gas cloud itself. In the X-ray image, the gas is not just sitting still. It has a distinct structure, with a leading edge that resembles a shock front. This is where the bullet aspect of the name comes from, a region where one cluster's gas appears to have moved through the other, compressing and heating the material in front of it. This feature gives us additional information about the speed and direction of the collision. It suggests that one cluster passed through the other at a relatively high velocity, creating a clear separation between components. And yet, even with all this information, the most important part remains invisible. The dark matter does not show up in optical images. It does not emit X-rays. It does not leave a direct visual trace. Its presence is revealed only through gravitational lensing, through the bending of light, through the distortions it causes in the images of distant galaxies. So in a sense, when astronomers saw the bullet cluster, they were not just looking at a single picture. They were combining multiple layers of observation, each one revealing a different aspect of reality. It's a bit like looking at a scene through different filters. One shows the visible objects, another shows heat, another shows structure beneath the surface. Only when you put them together do you get a fuller understanding of what is actually there. And what they found was something that did not fit neatly into existing expectations. The separation between gas and mass was too large, too clear, too consistent to be explained by ordinary matter alone. It pointed towards something else, something that moves with galaxies, not with gas, something that does not collide, does not slow down, does not emit light, something that makes up most of the mass in the cluster, yet remains unseen. At this point, the idea of dark matter is no longer just a theoretical solution to a set of equations. It becomes a necessary part of the explanation for what is observed, because without it, the three views, optical, X-ray, and gravitational lensing, do not align. With it, they do. And that alignment, that consistency across different methods of observation, is one of the strongest indicators in science that we are on the right track. Still, it's worth keeping in mind that this does not mean we fully understand what dark matter is. We know how it behaves in certain situations. We know how it influences gravity. We know how it distributes itself in clusters and galaxies. But its true nature, what it is made of, how it fits into the broader framework of physics, remains an open question. The bullet cluster does not answer those questions directly. What it does is something quieter, but just as important. It shows us that whatever dark matter is, it is real enough to separate from ordinary matter during a cosmic collision. It shows us that the universe contains components that do not behave like anything we are familiar with. And it gives us a rare glimpse of those components, not by making them visible, but by showing us where they are not. Once we accept that the mass does not follow the gas, once we see that separation clearly, a new question naturally follows. Why shouldn't it exist? Why did this particular observation stand out so strongly against expectations? And what exactly made this separation so convincing that it changed the way scientists think about the composition of the universe? There is a certain expectation that quietly sits underneath most of our thinking about the physical world. When something is massive, when it has weight, when it influences motion through gravity, we tend to assume it must be tied to something we can point to. A star, a cloud of gas, a cluster of galaxies. Something visible, something tangible, something that occupies a clear place in space. So when astronomers first began comparing the different observations of the bullet cluster, there was an unspoken assumption guiding their interpretation. Wherever the matter is, that's where the mass should be. It sounds almost too obvious to question. After all, in everyday life, mass and matter are inseparable. You don't have one without the other. If something has weight, you can usually see it, or at least detect it in some familiar way. But the bullet cluster quietly challenges that assumption. Because when all the observations are placed side by side, optical images, X-ray data, and gravitational lensing maps, they do not align in the way we expect. Instead, they separate. And not just slightly, not in a way that could be dismissed as measurement error or uncertainty, but in a clear, structured, almost unsettling way. Let's slow down and walk through that separation carefully. First, we have the galaxies. These are the points of light seen in optical images. They represent stars, entire systems of stars, moving through space largely unaffected by the collision. After the clusters pass through each other, these galaxies continue forward, forming two main groupings that are now positioned on either side of the interaction region. Then we have the gas. This is the hot X-ray emitting material that fills the space between galaxies. When the clusters collided, this gas interacted directly. It slowed down, compressed, and remained closer to the center of the collision. So already we see two components behaving differently. The galaxies move ahead, the gas lags behind. This alone might not seem too strange. After all, we've already discussed why this happens. Stars are sparse and pass through easily. Gas is continuous and interacts. But now we introduce a third element, mass. Not visible matter, not something directly seen in any wavelength, but the total gravitational mass inferred from lensing. And this is where the expectation begins to break. Because if you were to predict where the mass should be, based on everything we know about ordinary matter, you would likely place it with the gas. The gas contains most of the visible baryonic matter. It is the dominant component in terms of ordinary mass. It is the part that collided, slowed down, and concentrated in the center. So it seems reasonable to assume that the gravitational mass should peak there as well. But when the lensing data is analyzed, that is not what appears. Instead, the mass is concentrated around the galaxies, not the gas, not the region where most of the visible matter resides, but the galaxies, which pass through the collision with relatively little interaction. This creates a separation that feels, at first glance, almost impossible. Mass without corresponding visible matter without corresponding mass. It's as if the weight of the system has shifted away from where the substance appears to be. To make this clearer, imagine you're looking at a scene where two large clouds collide. You expect the densest part of the clouds to carry the most weight, to define the centre of gravity, but instead, the weight seems to follow something else entirely, something you cannot see directly. That's the kind of disconnect we're dealing with here, and it is not subtle. The separation is large enough to be measured clearly. The peaks in the mass distribution, as revealed by lensing, are offset from the peaks in the gas distribution by a significant distance. This is not a small discrepancy, it is a structural difference. Now at this point, scientists had a few options. One possibility was that the observations were somehow flawed. Maybe the lensing data was being misinterpreted. Maybe the X-ray images were incomplete. Maybe there was some systematic error that could explain the mismatch. But as more data was collected, as different teams analysed the cluster using independent methods, the same pattern kept appearing. The separation was real. Another possibility was that our understanding of gravity might need adjustment. There are theories, such as modified Newtonian dynamics, that attempt to explain the behaviour of galaxies and clusters without invoking dark matter. These theories suggest that gravity behaves differently on large scales, becoming stronger than expected under certain conditions. If that were the case, then perhaps the apparent extra mass in the bullet cluster could be explained without introducing invisible matter. But here's where the separation becomes especially important. Modified gravity theories generally tie gravitational effects to the distribution of visible matter. If you change the laws of gravity, the effects should still be centered on where the matter is. In other words, if the gas contains most of the ordinary matter, then even with modified gravity, the gravitational lensing signal should be strongest there. But it isn't. The lensing signal follows the galaxies, not the gas. This creates a serious challenge for those alternative explanations, because it suggests that the source of the gravitational pull is not where the visible matter is concentrated. Instead, it is located elsewhere, and that elsewhere corresponds exactly to where we would expect dark matter to be if it exists. Moving with the galaxies, passing through the collision without slowing down, remaining separate from the gas. This alignment is not just convenient, it is consistent with the behaviour predicted for dark matter. And that consistency is what makes the bullet cluster so compelling. It's not just that there is extra mass. It's not just that the mass is invisible. It's that the mass behaves differently from ordinary matter in a way that can be observed directly through its effects. It separates. It moves independently. It does not interact in the same way. If you take a moment to reflect on that, it changes the nature of the question entirely. We are no longer asking, is there extra mass in the universe? We are asking, why does that mass behave as if it is a completely different kind of substance? And once you ask that, the idea of dark matter becomes less of a speculative addition and more of a necessary component. Because without it, the separation in the bullet cluster becomes very difficult to explain. You would need a mechanism that allows visible matter to move one way, gravitational effects to appear somewhere else, and the two to remain consistently offset in a way that matches observations. So far, no alternative explanation has been able to do this as cleanly as the dark matter hypothesis. Still, it's worth noting that science rarely settles questions in a single moment. The bullet cluster did not instantly prove the existence of dark matter in a final, absolute sense. What it did was provide one of the clearest pieces of evidence that the idea is on the right track. It shifted the balance. It made certain explanations much more likely, and others much harder to sustain. And perhaps most importantly, it gave scientists a kind of visual confirmation, not of dark matter itself, but of its behaviour. You can almost think of it as watching footprints diverge from a visible path, revealing that something unseen is moving alongside what you can observe. The strange separation, then, is not just an odd detail. It is the central feature. It is the moment where expectation and observation part ways, where the universe quietly demonstrates that what we see is not all there is, and that the true structure of reality includes components that do not behave in familiar ways. There's something quietly reassuring about warmth. Even without seeing its source, you can often sense it. A cup of tea in your hands, sunlight through a window, the gentle heat of a room at rest. Heat feels familiar, almost comforting, something tied to everyday experience. But in the bullet cluster, heat takes on a very different role. It becomes something you cannot feel, cannot see directly, and yet something that reveals one of the most important parts of the entire event. Because while the galaxies passed through each other like distant travellers, and the invisible mass continued on without slowing, the gas told a completely different story, and it told that story through heat. To understand this, it helps to picture what this gas actually is. When we say gas in a galaxy cluster, we're not talking about something like air in a room. This gas is incredibly thin, far more diffuse than anything we encounter on Earth. If you were placed inside it, you wouldn't notice it in the usual sense. There would be no resistance, no feeling of pressure, and yet, despite being so sparse, it is extremely hot. We're talking about temperatures reaching tens of millions of degrees. At those temperatures, atoms are no longer intact in the way we're used to. Electrons are stripped away, leaving behind a plasma, a mixture of charged particles moving at very high speeds. This plasma doesn't emit visible light in a way our eyes can detect. Instead, it radiates energy in the form of X-rays. So even though it is invisible to us directly, it becomes visible through instruments designed to detect these high-energy wavelengths. And when astronomers looked at the bullet cluster in X-rays, what they saw was not just a diffuse cloud, but a structure, a shape, a pattern that held clues about what had happened. The gas appeared as a bright, glowing region concentrated between the two clusters of galaxies. It wasn't evenly distributed. It had a clear centre, a kind of dense core, and surrounding it were regions where the brightness changed gradually. But one feature stood out more than anything else. At the leading edge of one of the gas clouds, there was a sharp boundary, a sudden change in brightness and temperature, forming what is known as a shock front. If that term sounds a bit technical, it can be understood in a simple way. A shock front forms when something moves through a medium faster than disturbances in that medium can travel. It compresses the material in front of it, increasing its density and temperature. You might have seen something similar in everyday life, even if not in exactly the same form. The bow wave of a boat moving through water, the ripple that forms ahead of it as it pushes forward, or the way air compresses in front of a fast-moving object. In the bullet cluster, one of the clusters appears to have moved through the other, in such a way that its gas created a clear curved front, a region where the plasma was compressed and heated even further. This is where the bullet part of the name comes from. Not because anything was fired, but because the shape of this shock front resembles the leading edge of something moving through a medium at speed. And what's important here is not just the shape, but what it tells us. The presence of a shock front indicates that the gas experienced a significant interaction. It didn't pass through quietly. It slowed down, it collided, it heated up, and in doing so it left behind a visible trace of that interaction. This is very different from how the galaxies behaved. The galaxies show no such shock front. They don't compress or heat up in the same way. They simply continue on, their motion largely unaffected. So now we have another layer of contrast. The gas glows because it has been heated by interaction. The galaxies do not glow in the same way because they did not collide directly. And the dark matter, whatever it is, does not glow at all. But the gas does more than just glow. It carries information. By measuring the temperature, density, and distribution of the gas, astronomers can reconstruct aspects of the collision. They can estimate how fast the clusters were moving, how much energy was involved, and how the interaction unfolded over time. It's a bit like reading the aftermath of an event through the changes it leaves behind. The hotter the gas, the more energy was deposited into it. The sharper the shock front, the more clearly defined the motion was. The distribution of the gas tells a story of where matter slowed down, where it accumulated, where it lingered after the main passage. And all of this is happening on a scale that is difficult to fully appreciate. The region glowing in X-rays spans millions of light years. The energy involved is enormous, far beyond anything we can produce on Earth. And yet the processes themselves follow familiar principles. Compression leads to heating, interaction leads to resistance, motion through a medium creates structure. These are ideas we understand, just expressed on a much larger stage. What makes the glow of this gas so important is that it represents the ordinary matter, the part of the cluster that behaves in ways we expect. It collides, it slows down, it responds to pressure, it emits radiation when heated. In other words, it acts like matter we recognize, and because it behaves this way, it becomes a kind of reference point, a baseline. When we compare everything else to it, the differences become clearer. The galaxies, which pass through without significant interaction, already stand out, but the dark matter, which neither glows nor slows, becomes even more distinct. Because if the gas shows us how ordinary matter behaves under extreme conditions, then anything that does not behave like the gas must be something fundamentally different. And that is exactly what we see. The gas remains behind, glowing brightly, marking the region of interaction. The galaxies move ahead, visible but relatively unaffected. And the mass, as revealed by gravitational lensing, aligns with the galaxies, not the gas. So the glow of invisible heat does something subtle but crucial. It anchors our understanding. It shows us where the ordinary matter is. It shows us how that matter responds to a collision. And by doing so, it highlights the absence of similar behavior in the dark matter. Without the X-ray observations, the picture would be incomplete. We would see the galaxies, we would map the mass, but we would not have this clear glowing marker of where the interaction took place. We would not see the separation as clearly. The gas, then, acts almost like a tracer. It marks the path of the collision. It reveals the region where forces acted most strongly, and it provides a contrast against which the behavior of other components can be measured. It's also worth noticing how quiet all of this is. Even though the temperatures are extreme, even though the energies involved are enormous, there is no sound, no explosion, no dramatic flare visible to the human eye. The glow is steady, persistent, a silent record of an event that unfolded over millions of years, and that quietness is part of what makes it so easy to overlook. If you were to glance quickly at an image of the bullet cluster, you might see a bright cloud and a scattering of galaxies, without immediately grasping the significance of their arrangement. It takes time, careful observation, and the combination of multiple perspectives to understand what that glow really means. And once you do, it becomes clear that the gas is only part of the story. It shows us where matter collided. It shows us where energy was released. But it does not show us where most of the mass went. For that, we need to rely on something less direct, something that doesn't glow or emit, but still leaves an imprint, something that bends light itself. At some point, a quiet shift has to happen in the way we observe the universe. Up until now, most of what we've described has depended on light in one form or another. Visible light shows us galaxies. X-rays reveal hot gas. Even radio waves and infrared help fill in details about objects that might otherwise remain hidden. But what if something doesn't emit light at all? Not faintly, not dimly, not in some wavelength we haven't tuned into yet. Just not at all. That's where the usual tools begin to reach their limits, and where gravity becomes something more than just a force. It becomes a way of seeing, not in the traditional sense, not as an image or a colour, but as a pattern, a subtle distortion that reveals the presence of mass, even when that mass refuses to show itself directly. To understand how this works, it helps to step away from the complexity of galaxy clusters for a moment and think about something simpler. Imagine a beam of light travelling through empty space. If nothing interferes, it moves in a straight line, steady and predictable. But if that light passes near a massive object, its path bends slightly. This bending is not because the light itself is changing direction on its own, but because the space it is moving through is curved by gravity. This idea comes from Einstein's theory of general relativity, where gravity is not just a force pulling objects together, but a curvature in space-time itself. Massive objects distort the space around them, and light follows those distortions. So instead of moving in a straight line, the light takes a curved path. Now, if that bending is strong enough, it can produce noticeable effects. It can stretch the image of a distant galaxy, distort its shape, or even create multiple images of the same object. This phenomenon is called gravitational lensing. The name comes from the way a lens bends light, like the glass in a pair of glasses or a camera. But instead of glass, the lens here is mass itself. And this is where things become especially useful, because gravitational lensing does not care whether the mass is visible or not. It doesn't matter if the object emits light, reflects it, or absorbs it. If it has mass, it will bend light. That means gravitational lensing gives us a way to detect and map mass directly, without relying on visibility. In the context of the bullet cluster, this becomes incredibly important. We already have two clear pictures: the galaxies, seen in optical light, the gas, seen in X-rays. But neither of these tells us where all the mass is. For that, astronomers look at how the cluster affects the light from galaxies behind it. If you observe a field of distant galaxies through a massive cluster, those background galaxies will appear slightly distorted. Not dramatically, not in a way that jumps out immediately, but subtly. Their shapes might be stretched in one direction. Their orientations might be aligned in patterns that wouldn't occur naturally. These distortions are small, but they are consistent. And when you measure enough of them, across many background galaxies, you can begin to reconstruct the distribution of mass that caused them. It's a bit like looking at a sheet of fabric that has been gently pulled and warped. By studying how the threads are stretched, you can infer where the tension is strongest, even if you can't see what is pulling on it. In practice, this requires careful observation and analysis. Astronomers take deep images of the region, identify as many background galaxies as possible, and measure their shapes with precision. Then they compare those shapes to what would be expected if no lensing were present. The differences, small as they are, reveal the influence of the cluster's gravity. From there, they build a map, not of light, but of mass. And when this process was applied to the bullet cluster, the result was something that did not align with the visible images. The mass was not concentrated where the gas was. Instead, it formed two distinct regions, aligned with the galaxies that had moved ahead of the collision. This is where the idea of measuring the unseen becomes more than just a concept, because what is being measured here is not directly observed in any traditional sense. There is no glow, no emission, no signal that comes from the mass itself, only the way it bends light, only the way it distorts the images of distant objects. And yet, from those distortions, a clear structure emerges, two peaks of mass separated from the gas, moving with the galaxies. This is not something that could be easily dismissed as coincidence. The alignment is too precise, the separation is too clear, and the method itself, gravitational lensing, is well understood and widely tested. It works not just in this one case, but across many different systems. So what we have here is a consistent picture built from independent lines of evidence. The galaxies show one distribution, the gas shows another, and the gravitational lensing map shows a third, one that aligns with the galaxies rather than the gas. This combination is what gives the observation its strength, because it is not relying on a single type of data. It is not dependent on one instrument or one interpretation. It is the convergence of multiple methods, each pointing toward the same conclusion. And that conclusion is difficult to avoid. Most of the mass in the bullet cluster is not where the visible matter is. It is somewhere else, somewhere that does not emit light, somewhere that does not interact with the gas, somewhere that can only be detected through its gravitational influence. At this point, the idea of dark matter becomes less of a hypothesis and more of a necessity, because without it, there is no clear way to explain why the mass map looks the way it does. You would need a mechanism that allows gravity to act strongly in regions where there is little visible matter, while ignoring regions where visible matter is abundant, and that mechanism would need to produce consistent results across different observations, not just in the bullet cluster, but in other systems as well. So far, no alternative explanation has matched this behaviour as effectively as dark matter. But even beyond the implications for dark matter, there is something quietly remarkable about the method itself, the idea that we can map something invisible by observing how it affects light from objects even farther away. It's a kind of indirect vision, not seeing the object itself but seeing its influence on everything around it. And in a way it reflects a broader theme in science. We often learn about things not by observing them directly, but by studying their effects. We infer the presence of atoms from chemical reactions. We infer the existence of planets from the motion of stars, and here we infer the presence of dark matter from the bending of light. Each step requires careful measurement, careful reasoning, and a willingness to accept that not everything can be seen in the usual sense. And yet, the evidence builds, piece by piece, observation by observation, until a picture forms. In the case of the bullet cluster, that picture is unusually clear. The separation between components is large enough to be measured directly. The lensing signal is strong enough to map with confidence, and the alignment between mass and galaxies is consistent with the idea that something invisible is moving along with them. It's almost like watching a shadow move across a surface, even though the object casting the shadow is hidden. You don't see the object itself, but you can follow its path, trace its outline, and understand its motion. And once you notice that shadow, it becomes difficult to ignore, because it moves with purpose. It aligns with certain structures and not others. It behaves in a way that suggests there is something there, even if it remains unseen. As we continue, the focus begins to shift again, because now that we have a way to map the unseen, to trace the hidden mass through gravitational lensing, a new realization begins to settle in. This is not just a single event. The bullet cluster is not an isolated curiosity. It is part of a larger pattern, a broader story about the composition of the universe itself. Long before anyone could point to a single image and say, "This is it," the understanding of dark matter had been building quietly, almost cautiously, across decades of observations. It was never one dramatic discovery, not at first. It was more like a pattern emerging in the background, something that kept appearing no matter where astronomers looked. Galaxies rotated too quickly, clusters held together too tightly, light bent more than expected. Each of these observations hinted at something missing, something unseen, something that seemed to carry weight without revealing itself directly. But hints, no matter how consistent, still leave room for doubt. They invite alternative explanations. Maybe the measurements are off, maybe the models are incomplete, maybe gravity behaves differently on large scales. So for a long time, dark matter existed in that uncertain space between explanation and assumption. Useful, widely accepted, but not yet undeniable. And then came a moment, not sudden in time, but sudden in clarity. A moment where multiple lines of evidence aligned in a way that was difficult to reinterpret, difficult to dismiss, and even more difficult to explain without accepting that something invisible was truly there. That moment came from the bullet cluster. What made it different was not just the data, but the way the data separated into distinct layers, each telling a different part of the story. By the time astronomers had gathered optical images, X-ray observations, and gravitational lensing maps, they were no longer looking at a single picture. They were looking at three, each one representing a different aspect of the same system. And when those three pictures were placed side by side, something clicked. Not in a dramatic sense, not as a sudden revelation, but as a quiet realization that everything fit together in a very specific way. Let's revisit those 3 layers, but this time with that realization in mind. The galaxies visible in optical light had moved ahead of the collision. They passed through one another with minimal interaction, continuing on their paths. The gas, visible in X-rays, had collided and slowed down, remaining concentrated between the galaxies, and the mass, revealed through gravitational lensing, was not centered on the gas. It was centered on the galaxies. This alignment is the key, because if you imagine trying to explain this without dark matter, you quickly run into a problem. The gas contains most of the ordinary matter. It is the dominant component in terms of visible mass. If gravity were acting only on this matter, or if our understanding of gravity needed slight adjustments, the strongest gravitational effect should still be centered on the gas. But they aren't. Instead, the gravitational effects are strongest where there is relatively little visible matter, where the galaxies are. This is the moment where the pieces stop feeling like separate observations and start forming a single, coherent picture. Because now the behavior of each component makes sense in relation to the others. The gas slows down because it interacts. The galaxies move forward because they are sparse. And the mass follows the galaxies because it is made of something that does not interact like gas. Something that behaves more like the galaxies in terms of collision, but more like a continuous distribution in terms of gravity. Something that is present in large amounts, but does not emit light. At this point, the idea of dark matter is no longer just one possible explanation among many. It becomes the simplest explanation that fits all the observations at once, and that simplicity matters. In science, the explanation that requires the fewest additional assumptions, while still accounting for all the data, is often the one that gains the most traction. Because it doesn't just explain one thing, it explains everything together. The bullet cluster does exactly that. It shows that most of the mass is not where the ordinary matter is. It shows that this mass moves differently during a collision. It shows that this behavior is consistent with the idea of dark matter as something that interacts primarily through gravity. And it does all of this in a single system, observed with multiple independent methods. This is why many scientists describe the bullet cluster as one of the clearest pieces of evidence for dark matter. Not because it introduces a new idea, but because it confirms an existing one in a way that is difficult to reinterpret. It's like solving a puzzle where each piece had been found separately over time, but never quite fit together completely. And then suddenly, one configuration allows all the pieces to lock into place. The image becomes clear, and once you see it, it's hard to go back to seeing the pieces as unrelated. There's also something quietly compelling about the nature of this clarity. It doesn't come from seeing dark matter directly. It comes from seeing how everything else behaves in its presence. From noticing where mass is not. From observing how different components respond to the same event. It's a kind of indirect certainty. Not absolute, not final, but strong enough to guide the direction of research, to shape the questions scientists ask next, and to narrow the range of possible explanations. Of course, this doesn't mean the story ends here. Clarity in one area often opens up new questions in another. If dark matter is real, then what is it made of? Why does it interact so weakly with ordinary matter? How did it form, and how does it influence the evolution of the universe? The bullet cluster does not answer these questions. What it does is remove a layer of uncertainty. It shifts the conversation. Instead of asking whether dark matter exists, the focus begins to move toward understanding its properties. And that shift is significant, because it changes the nature of the investigation. It moves from speculation to exploration, from wondering if something is there to figuring out what it is. There's also a broader implication here, one that is easy to overlook. The realization that most of the mass in the universe is invisible, that it does not interact with light, that it behaves differently from the matter we are familiar with, changes how we think about everything else. It suggests that the structures we see, galaxies, clusters, the large-scale web of the cosmos, are shaped by something we cannot directly observe, that the visible universe is only a small part of the whole, and that understanding the universe requires us to look beyond what we can see. In a way, the bullet cluster acts as a bridge between the familiar and the unknown. It takes something we can observe, galaxies, gas, motion, and uses it to reveal something we cannot. It shows us that even when something is invisible, it can still leave a clear and measurable imprint on the world around it. And that imprint, when observed carefully, can lead to a deeper understanding of the universe. Not every discovery arrives with a clear introduction. Some ideas spend a long time in the background, quietly sporting explanations, filling gaps, helping things make sense without ever becoming the main focus. Dark matter was like that for many years. It was present in equations, discussed in research, accepted in a practical sense, but still slightly distant, still something that felt just out of reach. Then, gradually that distance began to shrink. By the time astronomers had studied galaxy rotation, cluster dynamics, and gravitational lensing in different contexts, dark matter had already earned a place in modern cosmology. It explained too many things too well to be ignored, and yet there was always a certain hesitation, a sense that something so fundamental should, at some point, reveal itself more directly. What the bullet cluster offered was not a direct sighting, not a glowing signal or a new particle appearing in a detector, but something just as meaningful. It gave dark matter a position, a location, a way of standing apart from everything else. And that is what brings it, in a quiet and understated way, into the spotlight. Up until this moment, most of the evidence for dark matter had been based on motion. Stars moving too fast, galaxies behaving in unexpected ways, light bending more than it should. These were all strong indicators, but they shared a common feature. They were indirect. They told us that something must be there, but not exactly where it was, not in a way that could be separated cleanly from ordinary matter. The bullet cluster changes that, because here, for the first time, we are not just inferring the presence of dark matter from how things move, we are seeing its distribution separated from the visible components of the system. The galaxies mark one location, the gas marks another, and the mass, mapped through gravitational lensing, marks a third. But instead of forming a single combined structure, these components are offset from each other. And the mass, the part that carries most of the gravitational influence, aligns with the galaxies, not the gas. This is the moment where dark matter stops being just a supporting explanation and becomes something more concrete. Not visible, still not something we can detect directly, but now something that occupies space in a measurable way. Something that can be mapped. Something that can be separated from ordinary matter under the right conditions. It's a subtle shift, but an important one. Because once you can point to a region of space and say, most of the mass is here, even though we cannot see it, the idea becomes much harder to dismiss. It moves from being an abstract solution to being part of the physical structure of the universe, and that structure behaves consistently. In the bullet cluster, the dark matter appears to have passed through the collision without slowing down, just like the galaxies. It did not collide like the gas. It did not heat up or emit radiation. It simply continued forward, guided by gravity, maintaining its distribution. This behavior is exactly what had been expected from dark matter based on earlier models. It interacts weakly, if at all, with itself and with ordinary matter. It does not experience pressure or friction in the same way gas does, and because of that, it can move through a collision without being significantly affected. Seeing this behavior play out in a real system adds a level of confidence that was difficult to achieve before. It's one thing to propose that dark matter should behave this way. It's another to observe a system where that behavior becomes visible through its effects. There's also something quietly interesting about how this spotlight works. It doesn't illuminate dark matter directly. It doesn't make it glow or become visible in the usual sense. Instead, it highlights the contrast. It shows us where dark matter is by showing us where it is not. The gas remains behind, glowing brightly in X-rays. The galaxies move ahead, visible but sparse, and the mass, inferred through lensing, sits with the galaxies, revealing the presence of something unseen. It's a bit like noticing an object not by its appearance but by the way it displaces everything around it. You don't see the object itself, but you see the pattern it creates, the way it shapes its surroundings, and in this case, that pattern is clear enough to stand out. By this point, the conversation around dark matter begins to shift. Instead of asking whether it exists, the focus moves toward understanding what it is. Because if it behaves in this consistent way, if it dominates the massive clusters, if it shapes the motion of galaxies and the bending of light, then it must be a fundamental part of the universe. And yet its nature remains unknown. It does not fit into the standard categories of matter we are familiar with. It is not made of atoms. It does not interact with electromagnetic forces in a way we can detect. It does not emit, absorb, or reflect light. So what is it? This question becomes more pressing once the existence of dark matter feels more certain, and it leads to a range of possibilities. Some theories suggest that dark matter is made of new types of particles, ones that have not yet been detected directly. These particles would interact through gravity and possibly through very weak forces, but not through the electromagnetic force. Others explore more complex ideas, including entirely new frameworks for understanding matter and energy. But regardless of the details, the bullet cluster provides a kind of anchor point, a reference. A system where the behavior of dark matter can be studied in relation to ordinary matter. It doesn't answer all the questions, but it helps narrow them down. It tells us what dark matter is not. It is not strongly interacting like gas. It is not confined to the same regions as visible matter. It does not slow down in collisions, and those constraints are valuable. Because in science, knowing what something is not can be just as important as knowing what it is. It helps eliminate possibilities. It guides experiments. It shapes the direction of research. There's also a broader implication here that extends beyond dark matter itself. The realization that most of the mass in the universe is invisible, and that it behaves differently from ordinary matter, changes how we think about cosmic structure. It suggests that galaxies and clusters are embedded within larger frameworks, shaped by dark matter halos that extend far beyond what we can see. That the visible universe is just one layer of a more complex system, and that understanding that system requires us to look beyond light, beyond direct observation, and into the subtle ways gravity reveals hidden structures. The bullet cluster in this sense acts like a turning point, not because it introduces a completely new idea, but because it makes an existing idea much harder to ignore. It brings dark matter out of the background and into a position where it can be studied more directly, even if it remains invisible. Once dark matter steps into this clearer view, the next question becomes unavoidable. If it behaves so differently from ordinary matter, if it passes through collisions without slowing, if it does not interact in familiar ways, then what exactly is it made of? And how can we begin to test those possibilities in a universe where most of the matter refuses to reveal itself directly? Try, for a moment, to explain the bullet cluster using only the kinds of matter we already understand. No new particles, no invisible components, nothing beyond atoms, gas, stars, and dust. Just ordinary matter behaving under the familiar laws of physics. At first, that might seem like a reasonable approach. After all, science often prefers the simplest explanation, the one that doesn't introduce new ingredients unless absolutely necessary. So it's natural to ask whether everything we've seen so far could be explained without invoking dark matter at all. If the universe could be understood using only ordinary matter, that would be a satisfying outcome. But as we begin to walk through that idea carefully, step by step, the explanation starts to stretch in ways that are difficult to maintain. Let's return again to what we actually observe. We see galaxies, which pass through the collision with relatively little interaction. We see gas, which collided, slowed down, and now sits between the galaxies. And we see the gravitational mass, mapped through lensing, which is not located with the gas, but instead aligned with the galaxies. If everything in the cluster were made of ordinary matter, then the distribution of mass should follow the distribution of that matter. That's the key assumption. Mass and matter go together. So where the matter is most concentrated, that's where the gravitational effects should be strongest. And in this case, the gas contains the majority of the visible ordinary matter, not the galaxies, not the stars, the gas. So if we were relying only on normal matter, the gravitational lensing signal should be strongest in the region where the gas is densest. But that's not what we see. Instead, the strongest lensing signal appears where the galaxies are, even though they contain less visible mass than the gas. This is the first major problem. The mass is not where the ordinary matter is. Now, one might try to adjust the explanation slightly. Perhaps there is more gas than we can detect. Maybe some of it is too faint, too diffuse, or hidden in a way that current instruments cannot fully capture. But this idea runs into limits very quickly. The gas in galaxy clusters is already studied in detail across multiple wavelengths. X-ray observations are particularly sensitive to this hot plasma, and they provide a fairly complete picture of its distribution. To account for the missing mass using only ordinary matter, you would need a vast amount of additional gas that somehow avoids detection in X-rays, while still contributing significantly to gravity. That's a difficult balance to maintain. Because if the gas is dense enough to contribute that much mass, it should also emit detectable radiation. And if it doesn't emit radiation, then it must be behaving in a way that is no longer consistent with ordinary matter. So the explanation begins to circle back on itself. You start with ordinary matter, but to make it fit the observations, you end up needing something that doesn't behave like ordinary matter anymore. Another possibility is to consider stars that are too faint to detect. Perhaps there are vast numbers of dim or non-luminous stars, objects that contribute mass but not much light. But again, the numbers required would be enormous, far more than what is consistent with our understanding of star formation and galaxy evolution. And even if such a population existed, it would still be subject to the same physical interactions as other forms of matter. During a collision like the one in the bullet cluster, these objects would not pass through unaffected in the same way dark matter does. They would interact, at least gravitationally, and potentially through other forces if they are part of a larger structure. They would not neatly separate from the gas in the way the mass distribution suggests. Then there is the idea of modifying gravity itself. Instead of adding new matter, perhaps the laws of gravity behave differently on large scales. This approach has been explored in various forms, including theories that adjust how gravity operates at low accelerations. In some cases, these theories can explain the rotation curves of galaxies without requiring dark matter. So it's reasonable to ask whether a similar approach could work for the bullet cluster. But here, the separation becomes a critical challenge, because modified gravity still ties gravitational effects to the presence of matter. Even if the strength of gravity changes, it still acts where matter is located. So if most of the ordinary matter is in the gas, then the gravitational lensing signal should still be centered there. But it isn't. The lensing signal is offset, aligned with the galaxies instead. This creates a mismatch that is difficult to resolve. You would need a theory of gravity that not only changes how strongly gravity acts, but also somehow shifts where its effects appear, separating them from the visible matter. And that is a much more complicated requirement. It's not just about adjusting equations, it's about explaining why gravity would behave differently in different regions of the same system, in a way that mimics the presence of an invisible mass component. So again, the explanation becomes strained. Each attempt to account for the observations using only ordinary matter introduces new complications, new assumptions, new layers of adjustment. And with each step, the explanation becomes less simple, less natural. In contrast, the dark matter explanation fits the observations in a more straightforward way. If there is a component of matter that does not interact electromagnetically, that does not collide like gas, that passes through the cluster along with the galaxies, then the separation makes sense. The gas slows down, the galaxies move ahead, and the dark matter, being collisionless, moves with the galaxies, carrying most of the mass. This produces exactly the pattern we observe. The mass aligns with the galaxies, the gas is left behind, the lensing signal reflects the distribution of this invisible component. What's important here is not just that dark matter explains the observations, but that it does so without requiring additional adjustments for each part of the system. It provides a single framework that accounts for multiple features at once, and that coherence matters, because in science, explanations are not judged only by whether they can fit the data, but by how naturally they do so. An explanation that requires fewer assumptions, fewer special conditions, and fewer adjustments is generally preferred. In the case of the bullet cluster, ordinary matter alone struggles to meet those criteria. It can be made to fit parts of the observation, but not all of them simultaneously, at least not without introducing new complexities. Dark matter, on the other hand, fits the overall picture more cleanly. That doesn't mean it is the final answer, it doesn't mean there are no open questions, but it does mean that, given the current evidence, it provides the most consistent explanation. There's also something quietly revealing about this process. It shows how scientific understanding evolves not just by adding new ideas, but by testing existing ones against observations, by asking again and again whether what we know is enough to explain what we see, and when it isn't, by being willing to consider that something new might be needed. In this case, the bullet cluster acts as a kind of test, a situation where different explanations can be compared directly against the same set of observations, and in that test, ordinary matter alone falls short, not because it is unimportant, but because it is incomplete. It accounts for part of the system, the gas, the stars, the visible structures, but it does not account for the majority of the mass, and that gap is where dark matter enters the picture. It might feel a little uncomfortable to question something as familiar as gravity. After all, it's one of the first forces we learn about. Things fall, objects attract, planets orbit. The rules seem steady, dependable, almost beyond doubt. But in science, even the most trusted ideas are occasionally set aside for a moment and examined more closely. Not because they are expected to fail, but because understanding deepens when we ask whether they truly hold in every situation. And when astronomers first encountered the strange behaviour of galaxies and clusters, the idea that gravity itself might need adjustment did not seem unreasonable. Because if stars are moving faster than expected, if galaxies are held together more tightly than visible matter can explain, then there are two broad ways to interpret that. Either there is more matter than we can see, or the rules governing gravity are different from what we assume. Dark matter represents the first option. Modified gravity represents the second. So before accepting the existence of an invisible substance that makes up most of the universe, it makes sense to ask whether the laws of gravity themselves might be incomplete. This line of thinking led to the development of several alternative theories, each attempting to explain the same observations without introducing dark matter. One of the most well-known of these ideas is called modified Newtonian dynamics, often abbreviated as MOND. The basic idea behind MOND is not to replace gravity entirely, but to adjust how it behaves under certain conditions. In everyday situations, like on Earth or within the solar system, Newton's laws of motion and gravity work extremely well. They predict motion with remarkable accuracy. But MOND suggests that at very low accelerations, such as those found at the outer edges of galaxies, gravity might behave differently. Instead of weakening as quickly as expected, it might remain stronger, allowing stars to move faster without requiring additional unseen mass. In some cases, this approach works surprisingly well. MOND can reproduce the rotation curves of many galaxies, explaining why stars far from the centre move at speeds that would otherwise seem too high. So for a time, it offered an appealing alternative. No need for dark matter, just a refinement of the laws we already have. But as observations expanded, especially at the scale of galaxy clusters, the picture became more complicated. clusters are not just larger versions of galaxies, they are more complex systems containing galaxies, gas, and large-scale gravitational interactions that extend over millions of light years. And in these systems, Mond and similar theories begin to struggle. Even with modified gravity, there often isn't enough visible matter to account for the observed behaviour, so additional assumptions are needed. Extra components, adjustments, refinements, and this is where the bullet cluster becomes particularly important, because it provides a situation where the distribution of mass can be mapped independently of the visible matter, not just inferred from motion, but directly traced through gravitational lensing, and in this case the separation between mass and ordinary matter creates a challenge that modified gravity has difficulty addressing. Let's walk through that slowly. If gravity behaves differently than expected, then the effects of that gravity should still be tied to where matter is located. Even if the strength of the force changes, it should act on the matter that is present. So if most of the ordinary matter is in the gas, then the gravitational effects should still be strongest in that region. The gas is where the mass is, or at least where the visible mass is. But in the bullet cluster, the strongest gravitational lensing signal is not located in the gas, it is located with the galaxies. And this creates a mismatch, because now the gravitational effects are appearing in regions where there is less visible matter, while being weaker in regions where there is more. To explain this using modified gravity, you would need a theory that not only changes how gravity behaves, but also changes where its effects appear relative to matter. And that is a much more demanding requirement. It's not just about adjusting equations, it's about explaining why gravity would act as if there is mass in places where there is little visible matter, and less strongly where there is more. Some extended theories have tried to address this by introducing additional fields or components that effectively mimic dark matter. But at that point, the distinction begins to blur, because if you introduce new elements that behave like unseen mass, even if you describe them in terms of modified gravity, you're moving closer to the concept of dark matter itself. So the question becomes less about whether gravity is wrong, and more about which explanation provides the simplest and most consistent account of the observations. In the case of the bullet cluster, the separation between gas and mass is difficult to reconcile with modified gravity alone. It requires additional layers of explanation, additional assumptions, and more complex mechanisms, whereas the dark matter explanation fits more naturally. The galaxies move forward, the gas slows down. The dark matter, being collisionless, moves with the galaxies, and the gravitational lensing reflects that distribution. This does not mean that modified gravity is entirely ruled out. Science rarely closes the door completely on alternative ideas. There may still be aspects of gravity that are not fully understood, especially when we consider extreme environments like black holes or the early universe. But it does mean that in this particular case, modifying gravity alone does not provide a complete explanation. There's also something quietly valuable about this process. Even if a theory does not ultimately explain all observations, exploring it can lead to deeper understanding. It forces scientists to test assumptions, to refine models, to look more carefully at the data. It keeps the conversation open, and in doing so, it strengthens the conclusions that do emerge. Because when an idea survives multiple challenges, when it continues to fit observations across different systems and scales, it gains credibility. Not as an absolute truth, but as the best explanation we currently have. The bullet cluster in this sense acts as a kind of filter. It allows different theories to be tested against a clear and specific set of observations, and in that test the idea of dark matter passes more easily than the idea of modified gravity alone. So the question, could gravity itself be wrong, remains an interesting and important one. But in this context, the answer appears to be more nuanced. Gravity, as we understand it, works remarkably well in many situations. And while it may still hold surprises, the behaviour observed in the bullet cluster suggests that the missing piece is not just a change in the rules, but an additional component, something that carries mass, something that moves independently of ordinary matter, something that reveals itself only through gravity. And that brings us back once again to the idea that most of the universe is made of something we cannot see, something that does not behave like the matter we are familiar with, but something that is nonetheless very real in its effects. A useful way to understand any scientific idea is to place it under pressure and see how it behaves. Not in a dramatic sense, not as a competition, but as a careful comparison between what a theory predicts and what the universe actually shows us. Modified Newtonian dynamics, or MOND, had already shown that it could handle certain situations quite well. In particular, it provided a way to explain the rotation curves of galaxies without introducing dark matter. Stars at the edges of galaxies move faster than expected, and a MOND adjusts the behavior of gravity in low acceleration environments to account for that. So when galaxy clusters began showing similar discrepancies, it was natural to ask whether MOND could extend its success to these larger systems. For a while, the answer seemed to be partially. In some cases, MOND could reduce the amount of unseen mass needed to explain observations, but it often couldn't eliminate it entirely. Clusters still appeared to require additional mass, even under modified gravity. This didn't immediately rule MOND out, but it did suggest that something more might be needed. And then the bullet cluster entered the picture. What makes this system different is not just that it contains missing mass, but that the distribution of that mass is separated from the visible matter in a very specific way. This is where the comparison becomes more focused. MOND, at its core, changes how gravity behaves depending on acceleration. It does not introduce new matter, at least not in its simplest form. Instead, it modifies the relationship between force and motion. So in a system like the bullet cluster, MOND would still tie gravitational effects to the distribution of visible matter, even if the strength of those effects changes. That's an important point. MOND can change how strongly gravity acts, but it does not inherently move gravity away from where matter is located. So if we look at the bullet cluster through that lens, we would expect the strongest gravitational effects to align with the densest regions of visible matter. And once again, that brings us to the gas. The gas contains most of the ordinary matter. It is concentrated between the galaxies. It is the part that collided and slowed down. So under MOND, even with modified gravity, the gravitational lensing signal should still be strongest in that region. But when astronomers map the mass using gravitational lensing, that is not what they find. Instead, the mass is concentrated around the galaxies, the regions where there is less visible matter, the regions that pass through the collision with minimal interaction. This creates a clear mismatch between what MOND would predict and what is observed. To reconcile this, MOND would need to be extended or modified further. And indeed, some versions of MOND have attempted to do this by introducing additional components, such as neutrino-like particles, or other forms of unseen mass that can contribute to gravity. But at that point, something interesting begins to happen. The theory starts to move closer to the concept of dark matter, because once you introduce an additional mass component that does not emit light and interacts weakly with ordinary matter, you're essentially describing something that behaves very much like dark matter, even if it arises from a different theoretical framework. So the distinction becomes less about whether dark matter exists, and more about how it is described. Is it a new type of particle? Is it an emergent effect of modified gravity? Is it something else entirely? These are still open questions. But the bullet cluster places a strong constraint on any explanation. It requires that whatever is producing the gravitational lensing signal must be able to separate from the gas during a collision and move with the galaxies. It must behave as if it does not interact significantly with ordinary matter. And it must carry most of the mass. These are not small requirements. They are specific, measurable, and tied directly to observation. And any theory that aims to explain the bullet cluster must satisfy them. In the case of MOND, this has proven challenging. Not impossible, but complicated. It requires additional assumptions, additional components, and more elaborate frameworks to reproduce the observed separation, whereas the dark matter explanation fits more naturally. Dark matter, as currently understood, is collisionless. It does not interact electromagnetically. It passes through other matter without slowing down significantly. So when two clusters collide, the dark matter halos move with the galaxies, while the gas lags behind. This produces exactly the separation we observe. There's also something quietly telling about how these explanations scale. MOND works well for individual galaxies, where the dynamics are relatively simple and the distribution of matter is more uniform. But as systems become more complex, as we move to clusters and interactions like the bullet cluster, the limitations become more apparent. Dark matter, on the other hand, provides a consistent framework across different scales. It explains galaxy rotation, cluster dynamics, gravitational lensing, and large-scale structure formation. Not perfectly and certainly not completely understood, but consistently. And consistency matters, because the universe operates across many scales, from small systems to vast structures. An explanation that works in one context but struggles in another needs to be adjusted or expanded. An explanation that works across multiple contexts gains strength. This doesn't mean the discussion is settled. There are still active debates, ongoing research, and new ideas being explored. Some scientists continue to refine modified gravity theories, looking for ways to account for observations like the bullet cluster, without relying entirely on dark matter. Others focus on detecting dark matter particles directly, trying to move from indirect evidence to direct measurement. Both approaches contribute to the broader understanding, but the bullet cluster remains a kind of benchmark, a test case, a system where different theories can be compared against a clear set of observations. And in that comparison, the separation between gas and mass stands out as a critical feature. It is not easily explained by modifying gravity alone. It strongly suggests the presence of an additional component, something that behaves differently from ordinary matter, something that moves independently during collisions, something that carries most of the mass. So when we consider MOND versus the bullet cluster, it is not so much a simple competition as it is an illustration of how theories are tested. Each idea is examined in the context of real observations. Each is asked to account for what we see, and the one that does so most naturally, with the fewest additional assumptions, becomes the more compelling explanation, at least for now. Looking out into the night sky, it's easy to feel as though we're seeing the universe as it truly is. Stars scattered across darkness, galaxies forming faint smudges of light, distant structures stretching farther than we can easily imagine. It feels complete, almost full. But that impression is quietly misleading, because what we see, even with the most powerful telescopes, is only a small fraction of what is actually there. This realization didn't arrive all at once. It emerged slowly, as different observations began to point toward the same conclusion. Galaxies moved in ways that suggested more mass than we could detect. Clusters held together more tightly than visible matter allowed. Light bent more strongly than expected. Each of these clues hinted at something missing, and as those clues accumulated, a new picture began to take shape. Not of a universe dominated by stars and gas, but of one where the majority of matter is invisible. The bullet cluster plays an important role in this shift in perspective, because it shows this imbalance in a particularly clear way. In that system, the visible components, the galaxies and the glowing gas, can be mapped directly. We can see where they are, how they move, how they interact. But when we map the total mass, most of it is not located where the visible matter is. Instead, it forms its own structure, aligned with the galaxies, but not confined to the regions where ordinary matter is concentrated. This separation is a small glimpse of a much larger truth. On cosmic scales, the matter we can see is not the dominant component. It is just one layer. To understand how this fits into the broader universe, it helps to look at how scientists estimate the overall composition of everything. By studying the cosmic microwave background, the large-scale structure of galaxies, and the expansion of the universe, astronomers have been able to piece together a kind of inventory. And that inventory is surprisingly uneven. Ordinary matter, the kind made of atoms, the kind that forms stars, planets, gas and people, makes up only about 5% of the total content of the universe. 5%. Everything we see, everything we are familiar with, every star that has ever shone, every galaxy that has ever formed, all of it fits into that small fraction. The rest is something else. About 27% is attributed to dark matter. And an even larger portion, roughly 68%, is something even more mysterious called dark energy, which is thought to drive the accelerated expansion of the universe. For now, we can set dark energy aside and focus on dark matter, because it is the component directly revealed by systems like the bullet cluster. If dark matter makes up such a large fraction of the universe, then it is not just an addition to the picture, it is the framework. It shapes how galaxies form, how clusters evolve, how matter is distributed across cosmic scales. Without it, the universe would look very different. In the early universe, small fluctuations in density began to grow under the influence of gravity. Regions that were slightly denser attracted more matter, becoming the seeds of galaxies and clusters. Dark matter, being abundant and interacting primarily through gravity, played a crucial role in this process. It began to clump together early on, forming large halos that provided the gravitational wells into which ordinary matter could fall. Gas cooled, stars formed, galaxies emerged. But the underlying structure was already there, shaped by dark matter. This means that when we look at a galaxy, we are not just seeing a collection of stars, we are seeing the visible part of a much larger system. A galaxy sits within a dark matter halo, an extended region of invisible mass that stretches far beyond the visible edges. The stars trace out only a small portion of that structure. The same is true for clusters. They are not just groups of galaxies held together by visible matter. They are embedded in even larger halos of dark matter, which dominate the total mass and influence the motion of everything within them. So when we say that the universe is mostly invisible, we are not speaking metaphorically. We are describing a measurable reality. Most of the matter does not emit light. Most of the mass is not directly observable, and yet it is essential for explaining the structure we do see. There is something quietly humbling about this. The idea that the familiar, the stars and galaxies we can observe, represent only a small fraction of the whole. That the majority of the universe exists in a form we cannot directly perceive, and that our understanding of it comes from careful observation, inference, and the subtle ways it reveals itself through gravity. The bullet cluster gives us a rare opportunity to see this invisible majority in action, not by making it visible, but by separating it from the visible components, by showing how it behaves differently during a collision, by allowing us to map its distribution independently. It's a kind of natural demonstration, a moment where the hidden structure of the universe becomes more apparent, not because it changes, but because the visible matter around it moves in a way that exposes the difference. And once you see that, it becomes difficult to return to the earlier, simpler picture. The universe is no longer just a collection of luminous objects floating in space. It is a layered system, with visible matter embedded within a much larger invisible framework. This also changes how we think about emptiness. Space, which often feels empty, is not truly empty. Even in regions where there are no stars, no visible galaxies, there can still be dark matter, contributing to the overall structure, shaping the motion of nearby objects. It's a presence that does not announce itself. It does not shine or glow, but it is there, quietly influencing everything around it. There's also an interesting contrast between how we experience the world and how the universe actually is. On human scales, What we see and what exists are closely aligned. Light reflects off objects, allowing us to perceive them directly. Our senses give us a fairly accurate picture of our immediate surroundings. But on cosmic scales, that alignment breaks down. What we see is only a small part of what exists, and understanding the rest requires tools, methods, and ways of thinking that go beyond direct perception. Gravitational lensing, for example, becomes a kind of extended sense. It allows us to detect mass not through light, but through its effect on light. X-ray observations reveal hot gas that would otherwise remain invisible. Each method adds a layer to our understanding, helping to build a more complete picture. And yet, even with all these tools, much remains unknown. We know dark matter exists through its effects. We know it dominates the mass of galaxies and clusters. We know it plays a crucial role in cosmic structure. But we do not yet know what it is made of. We do not know its exact properties. We do not know how it fits into the broader framework of physics. So while the universe is mostly invisible, it is not entirely unknowable. It reveals itself indirectly, through patterns, through motion, through gravity, and systems like the bullet cluster help bring those patterns into focus. They show us not just that something is missing, but how that missing component behaves. They allow us to move from vague inference to more precise understanding. And as we continue, the focus begins to shift once again. Because once we accept that most of the universe is made of something invisible, the next question naturally follows. What could that something be? What kind of matter behaves in this way, interacting so weakly with light and ordinary matter, yet exerting such a strong influence through gravity? Instead of asking where dark matter is, which we've already begun to map through its gravitational effects, a more difficult question quietly takes its place. What is it actually made of? That question sounds simple, almost straightforward, but it leads into some of the deepest uncertainties in modern physics. Because unlike stars or gas or planets, dark matter does not present itself in any familiar way. It does not glow, it does not absorb light, it does not leave behind a clear signature that we can isolate in a laboratory, at least not yet. And so, scientists have had to approach this question from a different angle. Not by observing dark matter directly, but by asking what kind of substance could behave the way we see it behave, a substance that carries mass, a substance that interacts through gravity, a substance that passes through ordinary matter without slowing down, a substance that does not emit or absorb light. From those constraints, a range of possibilities begins to emerge. One of the most widely discussed candidates is something known as a WIMP, which stands for Weakly Interacting Massive Particle. The name might sound a bit technical, but it describes the idea quite clearly. A particle that has mass, so it contributes to gravity, and one that interacts very weakly with other matter, so it doesn't collide or emit light in the usual ways. If dark matter is made of WIMPs, then it would exist all around us, passing through space, through planets, even through our own bodies, without leaving a noticeable trace. That might sound a little strange at first, but it follows naturally from the properties we've observed. In the bullet cluster, dark matter appears to pass through the collision unaffected. So whatever it is, it must interact very weakly with both itself and with ordinary matter. WIMPs fit that description. For a long time, they were considered one of the leading candidates, partly because they also arise naturally in certain extensions of particle physics, theories that attempt to go beyond the standard model. These theories predict new particles, some of which could have the right properties to account for dark matter, and because of that, many experiments have been designed to try to detect WIMPs directly. Deep underground detectors, shielded from background noise, are set up to look for rare interactions between dark matter particles and ordinary matter. The idea is that if a WIMP occasionally interacts with an atomic nucleus, it might produce a tiny measurable signal. So far, these experiments have not produced a definitive detection. They have placed constraints, narrowing down the range of possibilities, but the particles themselves remain elusive. Another candidate that has gained attention is something called an axion. Axions are much lighter than WIMPs and arise from a different set of theoretical ideas. They were originally proposed to solve a problem in quantum chromodynamics, the theory that describes the strong nuclear force. But over time, it became clear that they might also have the properties needed to account for dark matter. Axions would be extremely light, but very numerous. They would interact even more weakly than WIMPs, making them difficult to detect. And like WIMPs, they would not emit or absorb light in a way that we could easily observe. Experiments searching for axions take a different approach. Instead of looking for collisions, they often try to detect subtle effects, such as the conversion of axions into photons in the presence of a strong magnetic field. These experiments are delicate and challenging, but they represent another pathway toward understanding what dark matter might be. Beyond WIMPs and axions, there are other possibilities as well. Some theories suggest that dark matter could be made of sterile neutrinos, a type of neutrino that does not interact through the weak nuclear force in the same way ordinary neutrinos do. Others explore the idea of fuzzy dark matter, composed of ultralight particles that behave more like waves than individual particles on large scales. There are even proposals that dark matter might not be a single type of particle at all, but a combination of different components, each contributing to the overall mass of the universe. What all of these ideas have in common is that they attempt to match the observed behavior of dark matter. They must account for its gravitational influence. They must explain why it does not interact strongly with light. They must be consistent with observations like the bullet cluster, where dark matter appears to pass through a collision without slowing down, and they must fit within the broader framework of cosmology, explaining how structures form and evolve over time. At the same time, there is an important distinction to keep in mind. All of these candidates are still hypothetical. They are grounded in theory, supported by indirect evidence, but not yet confirmed through direct detection. So when we talk about what dark matter might be, we are exploring possibilities, not stating conclusions. And that exploration is ongoing. There is also something quietly fascinating about how different this kind of matter is from what we are familiar with. Ordinary matter interacts in many ways. It emits light, absorbs radiation, forms chemical bonds, creates structures that we can see and touch. Dark matter, by contrast, appears to interact primarily through gravity. It does not form atoms, it does not participate in chemistry, it does not clump together in the same way to form stars or planets. Instead, it forms large, diffuse halos, shaping the structure of galaxies and clusters without becoming part of the visible components. It's almost as if it exists alongside ordinary matter, influencing it, guiding it, but not merging with it. This raises deeper questions about the nature of matter itself. Why does ordinary matter interact in so many ways, while dark matter interacts so weakly? What determines these properties? Are there other forms of matter that we have not yet discovered, each with its own set of interactions? These questions extend beyond astrophysics into the realm of fundamental physics. They touch on the basic building blocks of reality, the particles and forces that define how the universe operates, and they remind us that our current understanding, while powerful, is still incomplete. The bullet cluster plays a role here as well, not by telling us what dark matter is made of, but by narrowing the possibilities. It shows us that dark matter does not behave like ordinary matter in collisions. It shows us that it does not interact strongly with itself or with gas, and that helps rule out certain candidates while supporting others. For example, if dark matter interacted strongly with itself, we would expect it to slow down during a collision, more like the gas, but in the bullet cluster it does not. It continues forward, suggesting that any interactions it has must be very weak. So even without knowing its exact nature, we can begin to outline its properties. It is massive, it is largely collisionless, it does not emit or absorb light, and it plays a central role in shaping cosmic structure. These constraints guide both theoretical work and experimental searches. They help scientists design experiments, interpret data, and refine models. They turn a broad question, what is dark matter, into a more focused investigation. And yet, despite all this progress, there is still a sense of openness, a recognition that the answer may not fit neatly into our current categories. That dark matter might be something entirely new, something that requires us to expand our understanding of physics. Not everything that matters makes a sound, and not everything that shapes the universe leaves behind a signal we can easily detect. Some of the most important influences are defined precisely by what they do not do. Dark matter belongs to that category. It does not glow. It does not scatter light. It does not absorb radiation in any way we can measure. And perhaps most strikingly, it does not seem to collide, at least not in the way ordinary matter does. This absence of interaction is not just a detail. It is the defining feature that allows dark matter to remain hidden, even while it dominates the mass of the universe. To understand this silence, it helps to compare dark matter with the kinds of matter we are familiar with. Ordinary matter interacts through several fundamental forces. Gravity is one of them, but there are others as well. Electromagnetism governs how atoms bond, how light is emitted and absorbed, how charged particles interact. The strong and weak nuclear forces operate at smaller scales, holding atomic nuclei together and allowing certain types of decay. These interactions are what make matter visible and tangible. When atoms absorb and emit light, we can see them. When particles collide, they produce heat, radiation, and other detectable effects. When gases compress, they heat up and glow, as we saw in the bullet cluster. But dark matter does not seem to participate in most of these processes. It interacts through gravity, yes, but beyond that, its interactions appear to be extremely weak or possibly non-existent. This is what allows it to pass through ordinary matter without slowing down. In the bullet cluster, this behavior is especially clear. The gas clouds collide, compress, and heat up, producing a bright X-ray signal. The galaxies pass through with minimal interaction, their stars rarely encountering one another. And the dark matter, whatever it is, moves along with the galaxies, unaffected by the collision. It does not slow down. It does not pile up. It does not produce any visible signal. It simply continues forward, leaving only its gravitational imprint behind. This is what we mean by the silence of dark matter. Not silence in the auditory sense, but in the sense of interaction. It does not announce itself through light or energy. It does not respond to collisions in a way that produces observable effects. It exists, but it does not speak in the language we're used to listening for. And that creates a unique challenge, because most of our tools for studying the universe rely on detecting interactions. We observe light across different wavelengths. We measure radiation. We detect particles produced in collisions. But if something does not interact in those ways, it becomes much harder to study. We are left with gravity as our primary tool. And while gravity is powerful, it is also subtle. It does not produce sharp signals. It does not create bright flashes or sudden events. It shapes motion, bends light, and influences structure over long timescales. So instead of seeing dark matter directly, we see its effects. We see galaxies rotating faster than expected. We see clusters holding together more tightly than visible matter allows. We see light bending around regions where there is no corresponding luminous object. And in the bullet cluster, we see mass moving independently of the gas, revealing a component that does not interact in the same way. All of these observations point to the same conclusion. There is something there. But it is quiet. It does not interact with light. It does not collide like ordinary matter. It does not produce signals that we can easily isolate. This silence also tells us something about the nature of dark matter itself. If it interacted strongly with ordinary matter, we would have detected it by now. It would scatter light, produce radiation, or show up in experiments more clearly. If it interacted strongly with itself, we would see evidence of that in systems like the bullet cluster. the dark matter would slow down, spread out, or behave more like the gas. But it doesn't. So whatever dark matter is, it must have very limited interactions beyond gravity. This constraint helps narrow down the range of possible candidates. It suggests that dark matter particles, if they exist, must be neutral, not carrying electric charge, and must interact very weakly with other particles. It also suggests that dark matter can move freely through space, forming large halos without collapsing into smaller, denser structures like stars. Because without electromagnetic interactions, there is no efficient way for dark matter to lose energy and condense. Ordinary matter can cool by emitting radiation. Gas clouds can collapse under gravity, forming stars and planets. Dark matter, lacking that mechanism, remains diffuse, spread out across large regions. This difference is what allows dark matter to form the extended halos around galaxies and clusters. It provides the gravitational framework but does not become part of the visible structures within it. There is also something interesting about how this silence affects our perception of the universe. If dark matter interacted with light, even weakly, the night sky might look very different. We might see vast halos surrounding galaxies glowing faintly. We might detect structures that are currently invisible. The universe might appear fuller, more crowded, more complex. But instead, much of that structure remains hidden. We see only the luminous parts, the stars, the gas, the galaxies, and we infer the rest from their behaviour. It's a bit like listening to a conversation where one participant is completely silent, yet clearly influencing the outcome. You don't hear their voice, but you see the responses, the changes, the adjustments, and from that, you begin to understand that they are there. The bullet cluster makes this particularly clear. The gas tells us where ordinary matter has interacted, the galaxies show us where visible structures have moved, and the gravitational lensing reveals where the mass is. When those three do not align, the silence of dark matter becomes noticeable. It is present, but it does not follow the same rules. It does not respond in the same way, and that difference stands out. As we continue, this silence becomes a guiding principle. It shapes how we search for dark matter. It influences the design of experiments. It defines the constraints that any successful theory must satisfy. Because whatever dark matter is, it must remain consistent with this lack of interaction. It must explain why we do not see it directly, why it does not collide like gas, why it does not emit or absorb light, and at the same time it must account for its strong gravitational influence. Balancing these properties is not simple. It requires careful thought, precise measurement, and a willingness to explore ideas that go beyond familiar categories. Once we understand that dark matter is silent in its interactions, the next question becomes how that silence plays out during events like collisions. What happens when two massive structures pass through each other, carrying this invisible component along? How does something that does not collide behave in a dynamic system? And how does that behaviour shape what we observe in the aftermath? Imagine motion without resistance, not just smooth motion like ice under a skate, but something even closer to perfect, where nothing pushes back, nothing slows you down, nothing takes energy away as you move. It's a difficult thing to picture because, in everyday life, almost everything involves friction in one form or another. Air slows us down. Surfaces resist movement. Even light in certain materials can be absorbed or scattered. Friction is so common that we rarely notice it unless it disappears. But in the bullet cluster, there is a component of the universe that behaves almost as if friction does not exist at all. And that component is dark matter. To understand why this matters, it helps to return once more to the moment of the collision, not as a single event but as a process unfolding over time. Two galaxy clusters approach each other, each carrying galaxies, gas, and dark matter. As they begin to overlap, each of these components responds differently. The gas, being made of charged particles, interacts strongly. It collides, compresses, and slows down. Energy is transferred. Heat is generated. The motion of the gas is disrupted. This is what friction looks like on cosmic scales. Not surfaces rubbing together, but particles interacting, exchanging energy, resisting motion. The galaxies, on the other hand, are mostly empty space. The stars within them are so far apart that direct collisions are extremely rare. As a result, the galaxies pass through each other with very little interaction. They experience gravitational effects, of course, but not the kind of direct resistance that slows the gas. So their motion continues, only slightly altered. And then there is dark matter. Whatever it is made of, it behaves even more freely than the galaxies. It does not collide like gas. It does not exchange energy in a way that produces heat or radiation. It does not experience friction in any measurable sense. So when the clusters pass through each other, the dark matter halos move forward almost as if nothing happened. They do not slow down, they do not pile up, they do not form shock fronts. They simply continue along their paths guided by gravity. This is what is meant by collisions without friction. Not that nothing happens, but that one component of the system moves through the interaction without the usual resistance. And this behavior is not just an interesting detail. It is a defining property, because it tells us something fundamental about the nature of dark matter. If dark matter interacted strongly with itself, or with ordinary matter, we would expect it to behave more like the gas. It would slow down, it would spread out, it would show signs of interaction, but it doesn't. So whatever dark matter is, it must have extremely weak interactions beyond gravity. This idea is often described using the term collisionless. A collisionless component is one that does not undergo significant interactions that change its motion through direct contact. In the context of the bullet cluster, dark matter appears to be collisionless. And that has important consequences, because it allows dark matter to maintain its structure even during a major event like a cluster collision. While the gas is disrupted and redistributed, the dark matter halos remain relatively intact, continuing forward with the galaxies. This creates the separation we observe: gas in the centre, galaxies and dark matter on either side, and the gravitational mass aligned with the latter. There's also something quietly revealing about how this lack of friction shapes the universe more broadly. Friction, in ordinary matter, allows structures to form in specific ways. Gas clouds can lose energy through radiation, collapse under gravity, and form stars. Collisions between particles lead to heating, pressure, and the formation of complex structures. But without friction, these processes do not occur in the same way. Dark matter cannot cool by emitting radiation. It cannot collapse into dense objects like stars or planets. Instead, it forms large, diffuse structures, extended halos that surround galaxies and clusters. These halos provide the gravitational framework, but they do not become part of the visible structures within them. So in a sense, dark matter shapes the universe from the outside. It sets the stage, it determines where matter can gather, but it does not participate in the detailed processes that create stars and galaxies. This separation of roles is part of what makes the universe so complex. Different components behave in different ways. Some interact strongly, forming visible structures. Others remain diffuse, influencing everything through gravity alone. And in the bullet cluster, this difference is made visible through the collision. The gas shows us what interaction looks like, the galaxies show us what sparse matter looks like, and the dark matter shows us what it means to move without friction. There's also a practical implication here. The fact that dark matter is collisionless places constraints on its properties. It suggests that any candidate particle must have very low interaction cross-sections, meaning it rarely interacts with other particles. It also suggests that dark matter does not form bound states in the same way ordinary matter does. These constraints help guide theoretical models and experimental searches. They narrow down the possibilities, even if they do not yet provide a definitive answer. At the same time, the idea of frictionless motion is not entirely absolute. Dark matter may still have some level of interaction, just very weak. There are ongoing studies that look for subtle effects, small deviations from perfect collisionless behaviour that could provide additional clues about its nature. But in systems like the bullet cluster, those effects, if they exist, are small enough that the overall behaviour appears frictionless, and that is enough to produce the observed separation. There's also something conceptually interesting about this. We often think of interactions as the defining feature of matter. Things collide, exchange energy, respond to forces. But dark matter challenges that idea. It shows that matter can exist in a form that interacts primarily through gravity, remaining otherwise silent and unaffected by most processes. It's a different kind of existence, one that is not directly tied to the familiar interactions we experience, and yet it is just as real in its effects. It shapes galaxies, it binds clusters, it influences the motion of everything around it, all without ever slowing down in the way ordinary matter does. If you were handed a map with most of its features missing, you might still be able to figure out what lies there by looking at how everything else is arranged. Roads bending around something unseen, rivers curving in unusual ways, empty spaces that suggest a presence rather than an absence. In a quiet sense, that is how much of the universe has been mapped, not by drawing what we can see, but by tracing the influence of what we cannot. By the time astronomers began studying systems like the bullet cluster, they already had tools that allowed them to do something quite unusual. They could create maps of mass, not just maps of light. And those two maps are not always the same. To understand how this works, it helps to return to the idea of gravitational lensing, but this time not as a single measurement, but as a method that can be applied across entire regions of the sky. When light from distant galaxies passes through the universe, it doesn't travel in perfectly straight lines. It moves through a landscape shaped by gravity, and wherever there is mass, visible or not, that landscape bends. Each galaxy cluster, each large-scale structure, acts like a subtle lens, distorting the images of objects behind it. Individually, these distortions are small. A galaxy might appear slightly stretched. Another might be tilted just a little more than expected. On their own, these changes are easy to miss, but when you look at thousands, even millions of galaxies, patterns begin to emerge, and those patterns can be analysed. Astronomers measure the shapes and orientations of background galaxies, comparing them to what would be expected in the absence of lensing. By doing this across large areas, they can reconstruct how mass is distributed in the foreground. This process turns subtle distortions into something much more tangible, a map, not of stars or gas, but of mass itself. And when these maps are created for systems like the bullet cluster, they reveal something that would otherwise remain hidden. The mass is not where the light is. Instead, it forms its own structure, aligned with the galaxies but extending beyond them, shaping the overall system in ways that are not immediately visible. This technique doesn't just apply to individual clusters, it can be used across much larger scales. By surveying large portions of the sky and measuring lensing effects over vast distances, astronomers can begin to map the distribution of dark matter across the universe. What emerges from these maps is not random, it is structured. Filaments of mass stretching between clusters, dense regions where galaxies gather, voids where relatively little matter is present. This large-scale structure is sometimes referred to as the cosmic web, and while the galaxies trace out parts of this web, the underlying framework is dominated by dark matter. It's as if the visible universe is draped over an invisible scaffold. The stars and galaxies mark the brightest points, but the full structure extends far beyond what we can see directly. There's something quietly remarkable about this. The idea that we can map something invisible, not by detecting it directly, but by observing how it shapes the light from objects even farther away. It requires a shift in perspective. Instead of looking for signals coming from the object itself, we look at how it influences everything around it. And from that influence, we reconstruct its presence. In the case of the bullet cluster, This method reveals two distinct concentrations of mass, aligned with the galaxies on either side of the collision. The gas, despite being bright in X-rays, does not correspond to the main mass peaks. This reinforces the idea that most of the mass is in a component that does not emit light. But beyond this specific example, mapping the invisible universe allows us to answer broader questions. How is matter distributed on the larger scales? How do galaxies and clusters form and evolve? What role does dark matter play in shaping the cosmos? These maps provide clues. They show that dark matter is not evenly spread out. It forms structures. It clumps together under gravity. It creates the conditions necessary for galaxies to form. Without it, the universe would look very different. Galaxies might not have formed in the same way. Clusters might not exist as we see them. The large-scale web might never have taken shape. So in a sense, mapping dark matter is not just about understanding an invisible component, it's about understanding the architecture of the universe itself. There's also an interesting contrast between how we perceive space and what these maps reveal. When we look up at the night sky, we see points of light scattered across darkness. It can feel sparse, almost empty. But when we map the distribution of mass, a different picture emerges. A connected network. Dense regions linked by filaments. Structures spanning hundreds of millions of light years. The universe is not empty. It is intricately structured, much of that structure hidden from direct view. And yet through careful observation we can begin to trace its outlines. The bullet cluster is one piece of this larger puzzle, a local example where the separation between visible and invisible matter becomes clear. But the same principles apply everywhere. In every galaxy cluster, in every region of the cosmic web, dark matter shapes the distribution of mass. And gravitational lensing provides the means to map it. Of course, this process is not without challenges. The distortions are small, the measurements require precision, the analysis involves complex models and careful statistical methods. But over time, as more data is collected and techniques improve, the maps become more detailed, more accurate, more revealing. They allow us to move from isolated observations to a coherent picture of the universe. And that picture consistently shows that most of the mass is invisible, consistently shows that dark matter forms the backbone of cosmic structure, consistently shows that what we see is only part of the whole. There's also something quietly philosophical about this. The idea that reality can be mapped not just by what is directly observed, but by the patterns it creates. That absence of light does not mean absence of substance. That invisibility does not mean insignificance. In fact, in this case, it means the opposite. The invisible component is the dominant one, and understanding it is essential for understanding everything else. Somewhere in the quiet background of everything we've discussed so far, there's a detail that hasn't been fully brought into focus yet. Not about what the bullet cluster is, or how it behaves, but when it happened. Because what we are looking at is not happening now. It only appears that way. The light reaching us from the bullet cluster has been travelling for hundreds of millions of years. By the time it arrives, carrying images of galaxies, gas, and subtle distortions from gravitational lensing, the actual event has already moved on. What we see is a snapshot from the past, and that realization changes the way we think about the entire scene. When we observe the bullet cluster, we are not watching a collision unfold in real time. We are seeing the aftermath of something that occurred long ago, frozen in the light that has just now reached us. This is always true in astronomy, but it becomes especially meaningful here, because it means the separation we observe, the gas left behind, the galaxies moving ahead, the dark matter aligned with them, is a moment captured mid-process. Not the beginning, not the end, but somewhere in between. If we could watch the full sequence, it would unfold over millions of years. The clusters would approach. Their outer regions would begin to overlap. The gas would start to interact, compress, and heat. The galaxies would drift through, largely unaffected. The dark matter halos would pass by each other, maintaining their structure, and then gradually everything would continue on. the separation increasing as the clusters move farther apart. What we see now is a single frame from that sequence, and yet that frame contains a remarkable amount of information. It shows us not just that a collision occurred, but how different components responded to it. It shows us the timing, in a sense. The fact that the gas is still concentrated between the clusters suggests that the interaction was relatively recent on cosmic timescales. The galaxies have moved ahead, but not so far that the connection is lost. The dark matter remains aligned with them, indicating that it has continued moving without significant disruption. So even though we are looking into the past, we can reconstruct the sequence of events. We can infer what happened before and what will happen after. This is one of the strengths of astronomy. Even without observing events directly as they unfold, we can piece together their history from the clues left behind. It's a bit like seeing footprints on a path and understanding the direction someone walked, even if they are no longer there. But in this case, the footprints are made of light, gravity, and the distribution of matter across millions of light years. There's also something quietly interesting about how common these kinds of events are. Galaxy cluster collisions are not rare in the universe. They happen as part of the ongoing evolution of large-scale structure. Clusters grow by merging with other clusters, by accreting smaller groups of galaxies, by interacting over long periods. So the bullet cluster is not a unique event. What makes it special is the clarity with which we can observe it. The angle of the collision, the separation of components, the strength of the lensing signal, all of these factors combine to create a particularly clear example. But there are other clusters at different stages of interaction. Some earlier in the process, where the components are just beginning to overlap. Others later, where the separation has increased or the structures have begun to merge more completely. By studying these systems together, astronomers can build a more complete picture of how such collisions evolve over time. They can compare different stages, they can look for consistent patterns, they can test whether the behaviour observed in the bullet cluster is part of a broader trend. And so far, the answer appears to be yes. In other colliding clusters, similar separations between gas and mass have been observed. Not always as cleanly, not always as dramatically, but enough to suggest that this behaviour is not an isolated case. This reinforces the idea that dark matter behaves consistently across different systems. It passes through collisions without significant interaction. It remains aligned with galaxies rather than gas. It forms structures that persist even as ordinary matter is disrupted, and that consistency is important, because it suggests that we are not just seeing a coincidence, not just a one-off event that happens to fit a particular explanation. We are seeing a pattern, a recurring behaviour that reflects an underlying property of the universe. There's also a deeper layer to this idea of time and observation. When we look at distant objects, we're always looking back in time. The farther away something is, the longer its light has taken to reach us, and the earlier in its history we are seeing it. This means that, in a sense, the universe provides us with a range of snapshots at different stages of evolution. Nearby objects show us more recent states. Distant objects show us earlier ones, and by combining these observations, we can build a kind of timeline, not by watching a single object evolve, but by comparing many objects at different distances and stages. The bullet cluster fits into this broader picture. It represents one point along that timeline, one example of how clusters interact, how matter behaves during those interactions, and how the structure of the universe evolves over time. And because of the clarity of this particular snapshot, it becomes a reference point, a system that can be studied in detail and compared to others, a kind of benchmark for understanding cluster collisions. There's also something quietly reflective about this. The idea that what we are observing is not happening now but has already happened, that the universe we see is always a step behind, always a record of past events, and yet that record is rich enough to reveal patterns, to allow us to reconstruct processes, to understand dynamics that unfold over timescales far beyond human experience. It reminds us that time in the universe operates very differently from time in our daily lives. Events that would seem impossibly slow on human scales are normal on cosmic scales. And yet, through careful observation, we can still make sense of them. We can still trace their outlines. We can still understand their implications. As we move forward, this idea of time continues to play a role, because the bullet cluster is not just a snapshot of a past event. It is part of an ongoing process, one that continues to shape the universe. Clusters will continue to collide, structures will continue to evolve, dark matter will continue to guide the formation of galaxies and the distribution of mass. And by studying these processes across different systems and different times, we can begin to see the larger picture. Not just what happens in a single collision, but how the universe as a whole changes and grows. If the bullet cluster were the only example of its kind, it would still be fascinating. A single, well-observed event where galaxies, gas and invisible mass separate in a way that reveals something fundamental about the universe. But what gives it even more weight is the fact that it is not alone. Across the sky, in different regions and at different distances, astronomers have found other clusters that appear to be going through similar interactions. Not identical, not perfectly matching in every detail, but close enough to suggest that what we see in the bullet cluster is part of a broader pattern. And once you begin to look at these other systems, the picture starts to deepen. Each one becomes a kind of variation on the same theme. Two or more clusters approach each other. Their galaxies pass through with minimal interaction. Their gas collides, slows down, and heats up. And the mass, mapped through gravitational lensing, does not always align with the gas. In some cases, the separation is clear and striking. In others, it is more subtle, requiring careful analysis to detect. But the underlying behavior is consistent. This consistency matters, because it suggests that the bullet cluster is not a rare anomaly, not a one-off event that happens to fit a particular explanation, but part of a larger class of phenomena, a natural outcome of how matter behaves on cosmic scales. One example that is often discussed alongside the bullet cluster is a system sometimes referred to as the train wreck cluster, a name that reflects the complexity of its structure. In this cluster, multiple components are interacting, creating a more chaotic arrangement of galaxies, gas and mass. The separation between these components is not as clean or symmetrical as in the bullet cluster, but it still shows signs that the mass does not perfectly follow the visible matter. In fact, in some regions, the mass appears to be offset in ways that are difficult to explain without invoking dark matter. Then there are other merging clusters where the collision is at an earlier stage. In these systems, the galaxies and gas have not yet fully separated. The interaction is still ongoing, and the components are more closely aligned. But even here, careful measurements can reveal differences in how the gas and galaxies behave. The gas begins to show signs of compression and heating. The galaxies continue their motion with less disruption. And over time, as the collision progresses, the separation becomes more pronounced. By studying clusters at different stages of interaction, astronomers can build a kind of timeline. Not by watching a single collision unfold, which would take far longer than a human lifetime, but by comparing different systems that represent different moments in the process. Some clusters show the initial approach, others show the moment of interaction, and some, like the bullet cluster, show the aftermath, where the components have already moved apart. This approach allows scientists to piece together the sequence of events, to understand not just what happens, but how it happens, and importantly, to test whether the behavior observed in one system holds true in others. So far, the answer appears to be yes. Dark matter, as inferred from gravitational lensing, consistently behaves in a way that is distinct from ordinary matter. It does not slow down like gas. It does not concentrate in the same regions. It moves with the galaxies, maintaining its distribution even as the visible components are disrupted. There are also clusters where the geometry of the collision is different. Not a direct head-on interaction, but a more angled encounter. In these cases, the separation between components can be more complex, with mass, gas, and galaxies distributed in less symmetrical patterns. But even in these situations, the same principles apply. Gas interacts and slows. Galaxies pass through. Mass does not always align with the gas. Each variation adds to the overall understanding. Each system provides another test case, another opportunity to compare observation with theory. And as more data is collected, as more clusters are observed in detail, the pattern becomes harder to ignore. It's not just one example, it's many. There's also something quietly reassuring about this repetition. In science, a single observation can be intriguing, but it is always treated with caution. Multiple observations showing the same behavior under different conditions provide stronger support. They reduce the likelihood that what we are seeing is a coincidence or an artifact of a particular system. They suggest that the underlying explanation is robust, that it applies across different environments and scales. In the case of colliding clusters, this repetition strengthens the case for dark matter, because it shows that the separation between mass and ordinary matter is not unique to the bullet cluster. It is a general feature of how clusters behave during collisions. At the same time, these other systems also introduce new questions. Not every cluster shows the separation as clearly. Not every interaction is as clean or easy to interpret. Some clusters have more complex structures, multiple interactions, or additional components that make the analysis more challenging. This reminds us that the universe is not uniform. It does not present the same scenario in exactly the same way every time. There are variations, complexities, and details that require careful study. And those variations can provide additional insights. They can reveal subtle differences in how dark matter behaves. They can test the limits of our models. They can highlight areas where our understanding is still incomplete. So while the bullet cluster stands out as a particularly clear example, it is part of a larger landscape. A universe where collisions between massive structures are common, where matter behaves in different ways depending on its properties, and where the invisible component, dark matter, consistently reveals itself through its gravitational effects. There's also a broader implication here. If dark matter behaves consistently across different systems, then it is not just a local phenomenon. It is a universal one, something that exists everywhere, shaping the structure of the cosmos on the larger scales. And that brings us back to the idea that the universe is mostly invisible, not just in one cluster, not just in a few systems, but everywhere. The same principles that apply in the bullet cluster apply across the cosmic web. Dark matter forms the scaffolding, ordinary matter follows, and the structures we see are built within that framework. Once you begin to accept that most of the universe is made of something invisible, something that does not behave like ordinary matter, the question naturally shifts from what the universe is to what it will become. Because the fate of the universe is not determined only by what we can see, it is determined by everything that exists within it. And if dark matter makes up such a large portion of the total mass, then it must play a central role in shaping the long-term evolution of cosmic structures. To understand this, it helps to step back and think about what drives change in the universe over very long time scales. Gravity is one of the key forces. It pulls matter together, allowing structures to form and grow. Galaxies merge, clusters collide. Larger and larger systems emerge from smaller ones. This process has been ongoing since the early universe, gradually building the complex web of structures we observe today. Dark matter is deeply involved in this process. Because it dominates the mass of galaxies and clusters, it provides the gravitational framework that guides their formation. Ordinary matter falls into the gravitational wells created by dark matter, forming stars, galaxies, and visible structures. So in a sense, dark matter sets the stage for everything else. But gravity is not the only factor at play. There is also the expansion of the universe. Since the time of the Big Bang, space itself has been expanding, carrying galaxies farther apart over time, and more recently this expansion has been accelerating, driven by what we call dark energy. This creates a kind of balance. On smaller scales, gravity pulls matter together. On larger scales, the expansion of the universe pushes structures apart. The interplay between these two effects determines how the universe evolves. Dark matter, by contributing most of the mass, strengthens the pull of gravity within galaxies and clusters. It helps keep them bound. It allows clusters to form and persist even as the universe expands. So when we think about the future of structures like the bullet cluster, dark matter is what ensures that they remain gravitationally connected. The galaxies may continue to move, the gas may eventually settle, but the overall system remains bound by the combined mass, most of which is invisible. Over time, clusters that collide will not simply pass through each other and disappear. They will interact gravitationally, slow down relative to one another, and eventually merge into a single larger cluster. This process can take billions of years. During that time, the visible components, galaxies and gas, will rearrange, settle, and evolve. The gas may cool and form new stars, the galaxies may change shape through gravitational interactions, and the dark matter halos will gradually merge, forming a larger, more massive structure. This is part of a broader trend in the universe. Structures grow over time, small systems merge into larger ones, clusters become superclusters, and the cosmic web becomes more pronounced. Dark matter is central to this growth. Because it does not dissipate energy through radiation, it remains in extended halos, continuing to influence the motion of matter over long timescales. But there is also a limit to this growth. As the expansion of the universe accelerates, driven by dark energy, regions that are not already gravitationally bound will move farther apart, eventually becoming isolated from one another. Clusters that are already bound will continue to evolve internally, but the formation of new large-scale structures will slow down and eventually stop. This leads to a future where the universe becomes more fragmented. Clusters remain as isolated islands of matter, separated by vast expanding regions of space. Within those clusters, dark matter continues to shape the internal dynamics. Galaxies may continue to merge, stars will evolve and eventually fade. But the overall structure remains held together by gravity. There's something quietly interesting about how dark matter influences this outcome. Because it does not interact like ordinary matter, it does not lose energy in the same way. It does not collapse into smaller, denser objects. Instead, it remains as a diffuse, extended component, maintaining the gravitational potential of galaxies and clusters. This means that even as visible matter changes, as stars burn out, as gas is used up or dispersed, the dark matter halos remain. They continue to define the structure of the system. In a very distant future, long after most stars have faded, these halos will still be there, invisible but still shaping the motion of whatever remains. So when we consider the fate of the universe, dark matter is not just a background component, it is a lasting one. It determines how structures form, how they evolve, and how they persist over time. There's also a connection here to what we've seen in the bullet cluster. The collision between clusters is part of this larger process of growth and evolution. It shows how structures interact, how matter behaves under extreme conditions, and how dark matter continues to influence the outcome. The separation we observe in the bullet cluster is temporary. Over time, the clusters will continue to interact, eventually merging into a single system. The gas will settle, the galaxies will redistribute, and the dark matter halos will combine. But the behavior we observe during the collision, the way dark matter moves without friction, the way it remains aligned with galaxies, will continue to play a role in how the merged system evolves. There's also something reflective about this. The idea that the invisible component of the universe, the part we cannot see, is what ensures the stability of the structures we do see. That the long-term fate of galaxies and clusters depends more on dark matter than on the luminous matter we are familiar with. It's a reminder that the most important influences are not always the most visible ones. and that understanding the future of the universe requires us to look beyond what we can directly observe. Even with everything we've uncovered so far, there's a quiet boundary we keep approaching, one that doesn't announce itself clearly, but becomes more noticeable the further we go. It's not a boundary in space, not something you could point to on a map of the universe. It's a boundary in understanding, because no matter how detailed our observations become, no matter how carefully we measure light, motion and gravity, there are still things we cannot access directly. Dark matter sits right at that edge. We can map where it is, we can measure how much of it there must be, we can observe how it behaves during events like the bullet cluster. But when it comes to what it actually is, we begin to reach the limits of what current methods can tell us. This is not unusual in science. Often, understanding develops in layers. First, we observe patterns. Then we build models that explain those patterns, and eventually we test those models in more direct ways. But sometimes there is a long gap between knowing that something exists and knowing what it is made of. Dark matter is one of those cases. The evidence for its existence is strong, built from many different observations across different scales: galaxy rotation curves, gravitational lensing, cluster dynamics, the cosmic microwave background. All of these point toward the same conclusion. There is more mass in the universe than we can see, and that mass behaves in a way that is consistent with dark matter. But knowing that something exists is not the same as understanding its nature, and that is where the limits begin to appear. Our instruments are designed to detect interactions: light, radiation, particles, energy exchanges. But dark matter, by its very nature, avoids most of these interactions. It does not emit light, it does not absorb it in ways we can measure, it does not collide in a way that produces clear signals. So the usual tools come up short. We are left with indirect methods. We infer its presence from gravitational effects. We map its distribution through lensing. We study its influence on structure formation. These methods are powerful, but they also leave room for uncertainty, because they rely on interpretation, on models, on the assumption that our understanding of gravity and cosmology is accurate. So there is always a layer of inference between what we observe and what we conclude. That doesn't make the conclusions weak, but it does mean they are not final. There is also the challenge of scale. The phenomena we are studying occur over enormous distances and timescales. We cannot recreate galaxy cluster collisions in a laboratory. We cannot manipulate dark matter directly. We can only observe what the universe presents to us and try to interpret it as carefully as possible. This creates a kind of asymmetry. We can test ideas about ordinary matter in controlled experiments. We can observe how particles behave, how forces interact, how systems evolve. But with dark matter, we are largely observers, not experimenters. We wait for rare interactions, design sensitive detectors, and hope to catch a signal that confirms its nature. So far, those signals have remained elusive, and that raises an interesting question. Is dark matter difficult to detect because we have not yet built the right instruments, or because it interacts so weakly that direct detection will always be challenging? Or is there something more fundamental about it, something that requires a different approach entirely? These questions sit at the edge of current research. They are not yet answered, and they remind us that even with strong evidence, there can still be uncertainty. There's also a broader implication here. The idea that there are aspects of the universe that we can infer but not directly observe challenges our intuition. We tend to associate knowledge with visibility. If we can see something, measure it directly, then we feel we understand it. But in many areas of science, especially at very large or very small scales, that direct connection breaks down. We learn through effects, through patterns, through indirect evidence. And that requires a different kind of thinking, one that is comfortable with uncertainty, one that accepts that understanding can be incomplete, that we can know something exists without knowing everything about it. The bullet cluster is a good example of this balance. It provides clear evidence that dark matter behaves in a certain way. It shows us where it is and how it moves, but it does not tell us what it is made of. It answers some questions while leaving others open, and that is often how progress works. Each discovery closes some gaps and opens new ones. Each observation adds clarity in one area and reveals complexity in another. So the limits we encounter are not just obstacles, they are also guides. They show us where to look next, what questions to ask, what experiments to design. They shape the direction of research, and they remind us that understanding is an ongoing process, not a final destination. There is also something quietly humbling about this. The realization that even with advanced technology, detailed observations and sophisticated models, there are still fundamental aspects of the universe that remain unknown. That the majority of matter is invisible, that its nature is still uncertain, and that our current understanding, while powerful, is only part of a larger picture. At the same time, there is also something encouraging, because each step forward, each new observation, each refinement of theory brings us closer, even if the full answer is not yet within reach. The bullet cluster itself was once just another object in the sky. Its significance emerged through careful observation, through the combination of different methods, through the willingness to look at the data in new ways. And in doing so, it helped shift our understanding of the universe. So the limits we encounter today are not fixed. They are temporary. They mark the edge of what we currently know, not the edge of what can be known. Picture yourself somewhere inside that vast interaction, not at the scale of a human body standing on a surface, but as an observer placed within the space of the cluster itself. There is no ground beneath you, no sky above you, no clear horizon, just a deep, quiet field of space, filled with distant galaxies and a faint, almost imperceptible glow of hot gas. At first, nothing would seem unusual. If you arrived before the collision reached its most active phase, the scene would feel calm, almost still. Galaxies would hang in the distance like scattered islands of light. The gas between them would be invisible to your eyes, even though it fills the space around you. There would be no sound, no wind, no sensation of motion. But slowly over time the view would begin to change. Not quickly, not in a way that draws immediate attention, but gradually, almost imperceptibly at first. The arrangement of galaxies would shift. New ones would appear from the direction of the approaching cluster. Their positions would change so slowly that, unless you were watching carefully over long periods, you might not notice. And yet, something would be happening. The clusters would be moving toward each other, drawn together by gravity. The distance between them would shrink, and the regions of space they occupy would begin to overlap. From your position, you might begin to notice that the background of galaxies is becoming more crowded. Patterns that once seemed stable would start to distort. Familiar alignments would shift. But there would still be no sense of impact, because the galaxies themselves would pass by at such great distances that collisions between stars would remain extraordinarily rare. Even as entire galaxies move through each other, the stars within them would continue along their paths, mostly unaffected. You might see a galaxy drift closer, its structure becoming more detailed, its spiral arms or elliptical shape more clearly defined. And then, over time, it would move past you, continuing on its way. There would be no shockwave, no explosion, no sudden change in brightness, just motion. Slow, steady, almost gentle. But if you had the ability to detect things beyond visible light, if you could somehow sense the gas that fills the space between galaxies, the experience would begin to feel different. As the clusters meet, the gas clouds would interact. They would not pass through each other quietly. They would compress, slow down, and heat up. If you could visualize that gas, you would see a growing region of density, a kind of invisible pressure building between the clusters, and within that region, temperatures would rise to millions of degrees. Not something you could feel directly, but something that would show up as a bright glow in X-ray wavelengths. From your perspective, this might appear as a growing luminous cloud forming between the two clusters, a region where matter is no longer moving freely but is being slowed, compressed, and heated by interaction. If you were able to track the motion of individual components, you would begin to notice a divergence. The galaxies continue forward, the gas lags behind, and something else, something you cannot see, continues along with the galaxies. This is where the experience becomes more subtle, because dark matter would be all around you, forming the dominant mass of the cluster, but it would not reveal itself in any direct way. You would not see it. You would not feel it in the usual sense. It would not glow or emit radiation. And yet, it would be there, shaping the motion of everything. If you were sensitive to gravity, if you could somehow perceive the curvature of space around you, you might notice that the regions where galaxies are moving ahead still carry most of the gravitational pull. Even though the gas, which appears more substantial, is left behind, this would be a strange realization that the visible concentration of matter is not where the majority of the mass resides, that something unseen is moving with the galaxies, carrying the gravitational influence forward. From your position inside the collision, this would not appear as a dramatic separation. There would be no line dividing one component from another. But over time, the differences would become more apparent. The gas would remain concentrated in the central region, glowing in X-rays. The galaxies would drift farther apart, forming two distinct groups, and the dark matter, though invisible, would continue to align with those groups, maintaining the structure of the clusters. If you could remain there long enough, watching over millions of years, you would see the separation grow. The clusters would move apart after the initial passage, then gradually slow under gravity, eventually beginning to fall back toward each other. The gas might settle, redistribute, and cool. The galaxies would continue their motion, influenced by the combined gravitational pull, and the dark matter halos would persist, merging slowly over time. What's striking about this imagined perspective is how quiet everything would be. Even though the energies involved are enormous, even though entire clusters are interacting, there is no sound, no explosion in the way we might expect. The motion is continuous, the changes are gradual. The most dramatic features, like the shock front in the gas, would still unfold over timescales far beyond human perception. So standing inside the collision would not feel like being in the middle of a crash. It would feel like being inside a slow transformation, a shifting landscape of galaxies and invisible structures evolving over time. And within that transformation, the most important component would remain hidden. Dark matter would pass through, unaffected, silent, shaping everything without revealing itself directly. You would not see it, but you would see its effects. The way galaxies move, the way gravity behaves, the way the structure of the cluster evolves. And from those effects, you would begin to understand that what appears empty is not empty at all, that most of what is there cannot be seen, that the universe operates on layers, some visible, some not, and that understanding those layers requires more than just looking. It requires interpretation, inference, and a willingness to accept that reality extends beyond what our senses can directly perceive. And now, at the end of this journey through the bullet cluster, through galaxies passing like ghosts, through invisible mass and silent motion, we can begin to step back and look at the larger picture. Not as a list of facts, but as a shift in perspective. Think again about what we started with. A simple question, in a way. What is the universe made of? At first, it feels like something we already know. Stars, planets, gas, dust. Everything we can see, everything that emits light. But as we followed the path of this collision, as we looked at galaxies moving through one another, as we saw gas slow down and glow, and as we mapped mass that could not be seen at all, that simple picture began to change. Not suddenly, not dramatically, but steadily, until it became clear that what we see is only a small part of what exists. The bullet cluster does not shout this conclusion. It doesn't present it as an obvious revelation. Instead, it shows it quietly through separation, through the fact that the gas and the mass are not in the same place, through the way galaxies move ahead while something invisible moves with them, through the way gravity reveals structures that light does not, and in doing so it invites a different way of thinking, a way of understanding the universe that does not rely only on what is visible, that accepts that most of the matter is hidden, that recognizes that the structures we observe are shaped by something we cannot directly perceive. There's something almost calming about that idea once you sit with it. The realization that the universe is not limited to what we can see, that there are layers, deeper structures, quiet influences that operate without drawing attention to themselves. It makes the cosmos feel larger, not just in size but in complexity, more complete, more intricate, and yet still understandable, piece by piece, through careful observation. If you imagine looking up at the night sky now, after everything we've discussed, it might feel slightly different. The stars are still there, the constellations still trace out familiar patterns, but behind them, around them, between them, there is something else, an invisible framework, a structure that does not shine, but still holds everything together. You won't see it directly, but you know it's there, in the way galaxies rotate, in the way clusters form, in the way light bends as it travels across the universe, and in the quiet separation revealed by a collision that happened hundreds of millions of years ago. There's also something gently humbling about this, the idea that even with all our instruments, all our observations, all our theories, we are still uncovering the basic composition of the universe, that something as fundamental as most of the matter around us can remain unseen for so long, and that understanding it requires patience, careful measurement, and a willingness to question assumptions that once seemed obvious. But at the same time, there is something reassuring, because even though dark matter is invisible, it is not unknowable. We can trace its presence, we can map its distribution, we can study its behavior, and with each observation, with each new piece of data, the picture becomes a little clearer. Not complete, not final, but clearer. And that is often how understanding works. It doesn't arrive all at once. It builds slowly, layer by layer, observation by observation, until what once seemed mysterious begins to feel familiar. If you find yourself drifting a little now, that's perfectly fine. This is not something that needs to be held tightly. It's something you can let settle in the background. The idea that the universe is mostly invisible, that what we see is just one layer, that beneath it, around it, there is a quiet structure shaping everything, and that even a single collision, observed from millions of light years away, can reveal something so fundamental. Before we gently fade out of this topic, there's just one small thing. If you found this journey calming, or interesting, or simply a nice space to think for a while, you can let that guide what you do next. Maybe you continue exploring. Maybe you rest. Maybe you come back to this later. There's no rush. The universe will still be there, still expanding, still evolving, still holding on to its quiet mysteries. And as you let your thoughts slow down, as the details soften and the bigger picture remains, you might notice one final idea lingering. That reality is often deeper than it appears, that what we cannot see can still shape everything we experience, and that sometimes the most important parts of the universe are the ones that remain completely silent, gently guiding everything from just beyond our view.